Now here the question is, let the sides of a triangle be decided by throwing a die thrice. If the probability that triangle is isosceles or equilateral is P by Q, where P and Q are relatively prime positive integers, then Q minus P is. Now, when we throw a dice thrice, then we'll get some numbers. In some cases, a triangle may be possible, and in other cases, a triangle is not possible. Now, what we'll do is we'll start counting number of equilateral triangles. Now, if we look at number of equilateral triangles, there'll be 6 cases when we have 1, 1, 1, 2, 2, 2, up to 6, 6, and 6. So there'll be overall 6 equilateral triangles. Now, next we'll consider triangles which are isosceles but not equilateral triangles. Now, with 1 we can only have 1, 1, 1. 1, 1, 2 will be a straight line. So the first isosceles triangle we'll get is with 2. So it'll be this 2, 2, 1. Then 2, 2, 2 will be an equilateral triangle. Then we'll have 2, 2, 3. Now 2, 2, 4 will be a straight line. And the same way we'll have 3, 3, 1, 3, 3, 2. Now 3, 3, 3 is equilateral. We'll have 3, 3, 4 and 3, 3, 5. 3, 3, 6 is again a straight line. Then we'll have 4, 4, 1, 4, 4, 2, 4, 4, 3. We'll discard 4, 4, 4. Then 4, 4, 5 and 4, 4 and 6. So we have 2 cases here, 4 cases here and 5 cases here. For 5 also we'll have 5 cases except for 5, 5 and 5. And for 6 also we'll have 5 cases here. So total number of isosceles triangles which are possible is 15 plus 6, and there'll be 21. Now if we look at scalene triangles, now for scalene triangle, if we consider smallest side as 1, then we'll get either an equilateral triangle or an isosceles triangle. There is no other way possible. Now we'll consider 2. Now if it is 2, then one of the triangle possible is 2, 3, 4. Now 2, 3, 5 is a straight line. And then we'll have 2, 4, 5. And also 2, 5, 6. And the same way smallest side is 3. Then we'll have 3, 4, 5. We'll also have 3, 4, 6. And then we'll have 3, 5, 6. And also it'll be this 4, 5, 6 considering smallest side is 4. So here we have 7 cases. So there'll be these 7 scalene triangles. Now total number of triangles that are possible will be this 6 plus 21 plus 7, which is 28 plus 6, 34. And out of these 34 triangles, the triangles which are either isosceles or equilateral, there are 6 plus 21, which is 27. So this required probability that triangle is either isosceles or equilateral will be this 27 by 34, which is given as P by Q. Now we need to find the value of Q minus P. Now 34 minus 7, it is 7. So answer to this question is 7. Now here the question is, let V and W be distinct randomly chosen roots of the equation z to the power 1997 minus 1 equals 0, and let m by n be the probability that root of 2 plus root 3 is less than or equal to mod of v plus w, where m and n are relatively prime positive integers. Find m plus n. Now basically these are nth root of unity. Now one of the root is 1, and then we have alpha square, if we find angle between any two successive roots and suppose that is theta, this angle is given by 360 divided by 1997. So that is the smallest possible unit of angle. Now we need to choose two roots v and w such that mod of v plus w is greater than or equal to root of 2 plus root 3. Now suppose we have two roots, say v and w, and angle between them is say alpha, then we can write mod of v plus w is greater than or equal to 2 plus root 3. Now we know that modulus of cube root of unity is 1. So this is 1 plus 1 plus 2 cos alpha and will be greater than or equal to 2 plus root 3. Now 2 and 2 will cancel. So from here we'll get this condition that cos alpha is greater than or equal to root 3 by 2, or from here we can say value of alpha should lie between 0 and 30 degrees. Now suppose we choose any one root, then for this condition to be true, we have to choose the other root so that this angle is less than or equal to 30. Now we need to find how many choices do we have for such cases. So it will be this 0 and then n times theta should always be less than or equal to 30. Now this is 0 and this is n, theta is 360 upon 1997 is less than or equal to 30. Now we simplify this, we'll get the value of n between 0 and 166.41. Now we cannot take 0 because then it will be the same root and n has to be integer. So we can choose this other root in 166 ways for this to be true. Now this angle, it can be either clockwise or it can be in the anti-clockwise direction. So we have 166 other roots in other direction. So total number of favorable ways in which mod of u plus w will be greater than or equal to root of 2 plus root 3 is given by 332. So for any root we have 332 favorable positions. So this required probability will be this 332 divided by, now how many total choices do we have? So there are 1997 roots, out of which one is v. So the remaining ones are 1996. So the required probability is 332 upon 1996, which is simply 83 by 499. And that is the answer to this question. Now the question is, there are 4 urns. The first urn contains 1 white and 1 black. Second one contains 2 white and 3 black. Third contains 3 white, 5 black. And fourth contains 4 white and 7 black. The selection of each urn is not equally likely. The probability of selecting ith urn is I square plus 1 upon 34. If we randomly select one of the urns and draw a ball, we need to find the probability of ball being white. Now first we are given that probability of selecting any ith urn, it is I square plus 1 upon 34. Now summation of pi, if you want to check, it will be this summation I square, where I varies from 1 to 4, plus summation 1, which is 4 upon 34. Now this is n plus 1, 2n plus 1 divided by 6 plus 4 upon 34. Now this is 3 and this is 2. So it will be 30 plus 4, 34. This is 1. So choosing the urns is a mutually exclusive and exhaustive process. Now once we have chosen any urn, we need to find the probability of ball being white. Now probability of ball being white, it is this summation probability of ball being white and has been chosen from ith urn, where I varies from 1 to 4. Now we can write this as pi into p w upon I, where I varies from 1 to 4. Now when the value of I is 1, this probability is 2 by 34,
And from the first turn, probability of getting a white ball is 1 by 2. For the second one, it'll be this 4 plus 1, 5, 5 by 34. And probability of getting white is 2 by 5. For the third one, this probability is 9 plus 1, 10, 10 by 34. And then getting a white ball is 3 by 8. Plus, when I is 4, it'll be this 17 by 34 into this probability of 4 by 11. And this value, it comes out to be 569 upon 1496, and that's your option A. Now here the question is, urn A contains 6 red and 4 black. So we have this urn A which contains 6 red and 4 black balls, and then we have this urn B which has 4 red and 6 black balls. Now one ball is drawn at random from A and placed in B. So we have taken one ball and we have placed it in B. Then one ball is drawn from urn B and placed in A. So we have taken one ball from B and we have put it back in urn A. If the one ball is now drawn from A, we need to find the probability that this ball is red. Now we'll start with this urn A, and in urn A we have 6 red and 4 black balls. Now one ball is transferred to urn B. Now this one transferred ball, it could be either red or black. Now the probability that it is red, it is given by 6 by 10, and it is black with the probability 4 by 10. Now if it is red, in urn B we have 5 red and 6 black, and if it is black, we now have 4 red and 7 black in B. So this is the position of B after the first transfer. Now again from B, we have transferred one ball back to A. Now if the ball transferred is red or black, and again here it could be either red or black. Now it'll be red with the probability 5 by 11 and black with the probability 6 by 11, and here it is red with the probability 4 by 11 and black with the probability 7 by 11. Now if it is red, we have 6 red and 4 black in A. If it is black and the first ball gone was red, so now we have 5 red and 5 black. Now previously, if black goes out from A and red comes in, it'll be 7 red and 3 black, and here it'll be 6 red and 4 black. So this is the configuration for A. Now from this, we need to find the probability that the ball drawn is red. Now here ball drawn is red with the probability 6 by 10. Here it is 5 by 10. Here it is 7 by 10. And here it is 6 by 10. So this required probability is sum of product of all these cases, which is 6 by 10 into 5 by 11 into 6 by 10 plus 6 by 10 into 6 by 11 into 5 by 10 plus 4 by 10 into 4 by 11 into 7 by 10 plus 4 by 10 into 7 by 11 into 6 by 10. And the denominator will have 1100, and here will be 6 into 6 into 5 2 times. So there will be 36 into 10, which is 360. And here we have 74, 28, 28 into 10, 280. Now we'll cancel this 0. So this is 36 plus 28, 64 divided by 110, which is 32 upon 55. And that's your option 1. Now the question is, a bag contains some white and some black balls, all combinations of balls being equally likely. The total number of balls in the bag is 10. If 3 balls are drawn at random without replacement and all of them are found to be black, find the probability that bag contains 1 white and 9 black balls. Now since we have already drawn 3 black, it means at least it should have 3 black balls. So let us say this bag has R black and 10 minus R white balls, where R varies from 3 to 10. Now each of these cases, they are equally likely. So we have total 8 cases. So probability that R is 3, R is 4 up to R is 10, it is 1 by 8 in each case. Now when we have R black and 10 minus R white, then the probability of choosing 3 black will be given by RC3 upon 10 C3. So this probability that we'll drop 3 black balls will be this summation 1 by 8, R varies from 3 to 10, RC3 upon 10 C3. Now it says, if it has already occurred, if you already know that 3 balls are black, find the probability that it contains 1 white and 9 black balls. So we have to find this probability that value of R is 9. So this probability that R is 9, given that the 3 balls are black, it is given by this case. This case is 1 by 8 into 9C3 upon 10C3 divided by 1 by 8 into this summation RC3 upon 10C3. Now 1 by 8 will cancel, 10C3 will also cancel. So we'll get this as 9C3, and here it will be 3C3 plus 4C3 up to 10C3. Now we can write this 3C3 as 4C4. Now n same R differs by 1, so it will be 5C4. Next one will be 6C4. So finally it will be this 11C4. So this required probability will be 9C3 upon 11C4. Now this is factorial 9, factorial 3, factorial 6, and here will be this factorial 11, factorial 4 and factorial 7. Now here will be this 4 into 7, and this one is going to be 11 into 10. So this probability will be 14 upon 55, and that's your option 1. Now here the question is, a bag A contains 4 red and 5 black balls, another bag B contains 6 red and 3 black balls, and a third bag C contains 3 red and 6 black balls. A bag is selected and a ball is drawn at random from the bags. If A, B, C denote the events of selecting bags A, B and C respectively, and E and F denote the events of getting red and black ball respectively, then find the following probabilities. Now we have 3 bags, A, B and C. Now A has 4 red and 5 black. B has 6 red and 3 black. And C has 3 red and 6 black balls. Now probability of choosing any one bag is 1 by 3, 1 by 3 and 1 by 3. Now probability of choosing this event E, which is getting a red ball. So probability of E by A is 4 by 9. E by B is 6 by 9 and E by C is 3 by 9. Now the first question is, we need to find this probability, which is probability of E upon A union B. Now probability of E upon A union B is
probability of getting a red ball if it is either A or B. Now we can write this as probability of A union B intersection E upon probability of A union B. Now choosing A and B, it is mutually exclusive event. So we can write this as probability of A intersection E plus probability of B intersection E upon probability of A plus probability of B. Now probability of A intersection E is 1 by 3 into 4 by 9 and B intersection E is 6 by 9 and PA plus PB is simply 2 by 3. Now 1 by 3 will cancel. Now this value is 10 by 9 divided by 2. So it will be this 5 by 9 and that's your option C. Now the second one is we need to find if it is a red ball, we need to find the probability that it has come from this bag A. Now this is nothing but Bayes theorem. So we'll take this case of A in the numerator. So it will be 1 by 3 into 4 by 9 upon, now this is 1 by 3 and here it is 4 by 9 plus 6 by 9 plus 3 by 9. Now 1 by 3 will cancel. This 9 will also cancel. Now this is 4 by 13 and which is your option A. And finally it is find the probability of getting a black ball. Now probability of getting a black ball is this 1 by 3. Now black from this is 5 by 9. From this one it is 3 by 9 and here it is 6 by 9. Now this is 14 by 27 and that's your option D. Now the question is we have two urns, urn 1 and urn 2. Urn 1 contains 4 white and 5 black balls. Urn 2 contains 3 white and 6 black balls. Now it says one urn is chosen at random and a ball is drawn. Its color is noted and replaced back to the urn. Again a ball is drawn from the same urn, color is noted and replaced. The process is repeated 4 times. And as a result, 1 ball of white color and 3 of black color are noted. Find the probability that chosen urn was urn 1. Now let this event be A. Now probability of choosing any urn, suppose probability of choosing urn 1 will be equal to probability of choosing urn 2 because they are equally likely and there will be 1 by 2. Now if we choose urn 1, then probability of getting a white ball and 3 black balls will be probability of A by U1 and it will be 4C1 into, now probability of white is 4 by 9, probability of black is 5 by 9. So there will be 4C1 4 by 9 into 5 by 9 cube. Now the same way for the second urn, again we have 1 white, so there will be 4C1. Now here probability of white is 3 by 9 and probability of black is 6 by 9. So there will be 6 by 9 whole cube. Now it's a Bayes theorem question. So it says if this event has already occurred, we need to find the probability that chosen urn was urn 1. So we need to find probability of having urn 1 if A has already occurred. So we'll take this case in the numerator. So it will be this 1 by 2 and 4C1. This is 4 by 9 into 5 by 9 cube upon 1 by 2 into 4C1, 4 by 9, 5 by 9 cube plus 1 by 2 into 4C1, 3 by 9 into 6 by 9 whole cube. Now 1 by 2 4C1 will cancel and this 9 to the power 4 will also cancel. So this result will be this 4 into 5 cube plus 4 into 5 cube plus 3 into 6 cube. Now this is 500 upon 500 plus 648
which is 500 upon 1148. And if we simplify this, it comes out to be 125 upon 287. So basically this problem, it is a mix of binomial probability, because we are replacing the ball every time, and Bayes theorem. Now here the question is, a letter is known to have come from either Krishnagiri or Dharmapuri. On the postmark, only 2 consecutive letters RI are visible. Then the chance that it came from Krishnagiri is, we have 2 events, either it can come from this Krishnagiri or it can come from Dharmapuri. Let us say this event K is, it has come from Krishnagiri, and event B, that it has come from Dharmapuri. Now, getting a letter from either of these 2 places is equally likely. So this probability, it is 1 by 2, and this probability is also 1 by 2. Now let us take this event A, that the 2 consecutive letters visible are RI. So if we find this probability, that probability A by K and LB. Now if we look at Krishnagiri, the possible 2 combinations are, so we have to choose any 2 consecutive, and we know that in a row, number of consecutive selections is given by n minus r plus 1. Now in this case, n is 5 and 5, 10, 11. 11 minus 2 plus 1. That will be 10 ways. And our favorite case is when Ri is visible. Now we get Ri here, and we also get Ri here. So this probability will be simply 2 by 10. Then the same way, if we look at Ri in Dharmapuri, now here we have 5 and 5, 10. So here it will be 10 minus 2 plus 1, which is 9. And from these 9, the favorable condition is only 1. So it will be this 1 by 9. Now it's a Bayes theorem question, that we know that if the letters Ri are visible, then it has come from Krishnapuri. So we'll take this case in the numerator. So it will be this 1 by 2 into 2 by 10 upon 1 by 2 into 2 by 10 plus 1 by 2 into 1 by 9. Now this 1 by 2 will cancel. Now this is 1 by 5, and this is 1 by 5 plus 1 by 9, and will be this 9 by 14, and that's your option C.
Now here the question is, 6 different balls are put in 3 different boxes, none being empty. The probability of putting the balls in equal number is. Now we have 3 boxes, and they're different, say first, second, and third. Now how can we put the balls in them so that none of them is empty? Now what we'll do is, first we'll figure out in how many ways we can distribute the balls so that none of the box is empty. Now either it could be 4, 1, 1, or it could be 3, 2, 1, or it is 2, 2, and 2. So these are the 3 possible cases. Now first we'll distribute them as 4, 1, 1. It can be done in factorial 6 divided by factorial 4. Now since we have 2 ones, it will be this factorial 2, and then we can arrange these 3 groups in 3 boxes in factorial 3 ways. Now this is 13 to 3, 90. So there are 90 ways possible. Now how about 3 to 1? It will be this factorial 6 divided by factorial 3, factorial 2. Now again we have to distribute them in 3 boxes. Now it will be this factorial 3 gets cancelled. Then it will be this 360. And finally this is factorial 6. Then factorial 2 3 times divided by factorial 3, and then we'll multiply it with factorial 3, which will get cancelled. Now here it will be again 90. Now we need to find the probability that the balls are put in equal numbers. So this required probability will be, this is the favorable case, 90 upon total. Now total will be 90 plus 90, 180, 180 plus 360, and that will be 540, which is 1 by 6. So this A it matches with Q. Now the second one is 6 letters are posted in 3 letter boxes. Find the probability that no letter box is empty. Now we have to find the probability that no letter box is empty. Now first we'll find total number of ways of distributing these 6 letters in these 3 letter boxes. Now for each letter we have 3 choices. So total number of ways of distributing these 6 letters in 3 boxes is 3 to the power 6. Now in how many ways we can distribute them so that no letter box is empty? Now this case is similar to this first one, where we have 6 different balls in 3 different boxes such that none of them is empty. Now total number of ways of doing it is 540. Now in this case, this 540, it becomes our favorable case. So this probability will be this 540 divided by 3 to the power 6. Now 9, so this is 60 and this is 3 to the power 4. Now this is 20 by 27. So this B, it matches with B. Now in the third one it says 2 persons A and B throw 2 dice each. If A throws a sum of 9, then probability of B throwing a sum greater than A is. Now we need to find this conditional probability that B throwing a sum greater than 9 if A has scored 9. Now this probability is probability of A throwing 9 and B throwing sum greater than 9 divided by probability of A throwing 9. Now we'll get 9 in a throw of 2 dice if we have 3, 6, 4, 5, 5, 4 and 6, 3. So this required probability of A9 will be simply 4 by 36. Now we need to find this intersection that A scores 9 and B scores the sum which is greater than 9. Now the sum greater than 9 could be either 10 or 11 or 12. Now we get 10 if we have 4, 6, 5, 5 and 6, 4. 11 is 5, 6, 6, 5 and 12 is 6, 6. So we have 6 cases here. Now A9 intersection B as greater than 9. Both these events, they are independent events. So there is no correlation between A getting 9m and B getting sum greater than 9. So it will simply be probability of A9 which is 4 by 36 into probability of B getting sum greater than 9 and which is 6 by 36. So this required probability will be simply 1 by 6. So that means this C, it matches with Q. And then it is if A and B are independent and PA equals 0.3 and P A union B naught, it is 0.8, find probability of B. Now we know that we can write probability of A union B naught as probability of A naught intersection B naught, and this is 0.8. So from here we can write probability of A naught intersection B will be simply 0.2. Now this is probability of A naught into probability of B and this is 0.2. Now probability of A naught, it is 0.7. So probability of B will be simply 2 by 7. That means this D, it matches with S. And that is the answer to this question. Now here the question is, a consignment of 15 record players containing 4 defectives is examined. The record players are selected randomly one by one without replacement. Now which of the following is or are correct? Now the first one is probability of getting exactly 3 defective in the examination of 8 record players. Now if we examine 8, so this probability will be 15 C8. Now are these 8? Exactly 3 are defective. So that should be 4 C3 and then remaining 5, it should be good. So there will be 11 C5. That means this option A is correct. Now this option B is probably the 9th one examined as last defective. Now we have 1 to 8 chances and then we have this 9th one. Now in 1 to 8 we should have 3 defective and 5 non-defective, and this 9th one, it has to be the last defective one. Now from 1 to 8 we have already worked out in this first case. So it will be this 4C3 into 11C5 upon 15C8. Now this ninth one has to be defective. Now we have 7 remaining. Out of these 7 remaining, 1 is defective. So this ninth one defective will be this 1 by 7, and that's the required probability. Now we need to simplify this. Now 4C3 is simply 4. Now this is factorial 11, factorial 5, factorial 6. Now this is factorial 15, factorial 8, factorial 7 into 1 by 7. Now this is 4. Now this 8 we can write this as 8 into 7, we'll cancel it with factorial 6, and 7 we'll write this as 7 into 6. And here will be this factorial 15, so will be 15, 14, 13 and 12 into 1 by 7. Now this 7 will cancel. Now 7, 14, 2, 12. So it will be simply 8 divided by 15 into 13, which is 195. That means this option B is also correct. Now C is probability that ninth examined player is defective, given that there were 3 defective in the first 8 is 1 by 7. Now in this, we need to find this conditional probability, which is probability of ninth examined. It is defective given that there were 3 defective in first 8, which is this first case. So it will be this A. That will be this probability of A intersection ninth upon probability of A. Now probability of A intersection ninth is nothing but this second case, which is this B. Now this probability is 4C3, 11C5, 15C8 into 1 by 7 divided by this probability of A, which is again this probability. So if everything gets cancelled, we'll get this as 1 by 7. So that means the statement C is also correct. And D is probability the ninth examined player is last defective is 8 by 197, which is wrong, which we have already worked out in this option B. So the correct options are A, B and C. Now the question is, a player throws an ordinary die with face numbered 1 to 6. Whenever he throws 1, he gets an additional throw. We need to find the probability of obtaining a total score n. Now first is when the value of n is 5. Now if n is 5, this player, he can score 5 if he either throws 5 or he throws 1 followed by 4 or 1, 1, 3 or 1, 1, 1, 2. These are the only possibilities. It cannot be 1, 1, 1 and 1, because after 1 he'll get another chance. Now probability of throwing 5, it is 1 by 6. Now this is 1 by 6 into 1 by 6. This is 1 by 6 cube, and this is 1 by 6 to the power 4. So that's the required probability now, which is 1 by 6, 1 minus 1 by 6 to the power 4 divided by 1 minus 1 by 6. Now this is 6 to the power 4 minus 1 upon 5 into 6 to the power 4. That means this option A, it is correct, and option B will be incorrect. Now if the value of n is 7, it will be this 1, 6 or 1, 1, 5, or it will be this 1, 1, 1 up to 2. Now here we have 1 upon 6 square, 1 upon 6 cube up to 1 upon 6 to the power 6. Now this is 1 upon 6 square, 1 minus 1 upon 6 to the power 5 upon 1 minus 1 upon 6. Now this is 6 to the power 5 minus 1, and this is 5 into 6, 30 upon 6 to the power 5. That means this option C is also correct. So the correct options are A and C. Now here the question is, 10 boys and 2 girls are divided into 3 groups of 4 each. Now the probability that the girls will be in different groups is, now what we'll do is, first we'll find total number of ways to distribute them. Now total number of ways in which we can distribute them in 3 groups of 4 will be factorial 12 divided by factorial 4 3 times and then factorial 3. Now we need to find this favorable case when the girls are in different groups. So what we'll do is we'll actually take up these 10 boys and we'll distribute them in a group of 4 3 3, and it can be done in factorial 10, factorial 4, factorial 3 square into factorial 2, and now we can distribute 2 girls in these 2 groups in factorial 2 ways. So now these 2 girls, they'll be in separate group. So this required probability will be this factorial 10 divided by factorial 4 factorial 3 square upon factorial 12 factorial 4 cube and factorial 3. Now this is factorial 10 factorial 4 factorial 3 and here it is factorial 12 and this is factorial 4 factorial 4 factorial 4 and this is factorial 3. Now factorial 4 will cancel, factorial 3 will cancel. Now this is 3 into factorial 4, we'll have 4 here, and this is factorial 10, it will be this 12 into 11, and factorial 4 is 4 into 3 into 2. Now here 12 will cancel. So this probability will be simply 8 by 11, and that's your option 4. Now we need to find the probability that birthdays of 6 different persons will fall in exactly 2 calendar months. Now total number of ways, for each person we have 12 choices. So it could be any one of the 12 months. So there will be 12 into 12 into 12, 6 times. So 12 to the power 6. Now the probability that birthday of 6 different persons will fall in exactly 2 calendar months. So which 2? It can be selected in 12C 2 ways. Now for each person we have 2 choices. So it will be 2 into 2 into 2, 6 times, and then minus 2 cases when we have all the 6 in any one month. So there will be 2 to the power 6 minus 2. So answer to this question is 12C2 2 to the power 6 minus 2 upon 12 to the power 6, and that's your option 3. Now the question is, there are 3 urns, red, white and green, containing as many red, white and green balls. That says a coin when tossed is twice as likely to come heads as compared to tails. So on this coin, probability of head is 2 times probability of tails. Now sum of 2 probabilities is 1. So clearly probability of getting a tails, it is 1 by 3, and probability of getting a heads is 2 by 3. Now it says such a coin is tossed 2 times. If both head and tails are present, then 3 balls are simultaneously drawn from urn 1. If head appears on both, then 3 balls are drawn in similar manner from urn 2, and if no heads appear, then the 3 balls are drawn from urn 3. Now we need to find the probability that 3 drawn balls are 1 each of different colors. Now suppose this is event A. Now it's a conditional probability question. So either the 3 balls, they can come from either urn 1, urn 2 or urn 3. So we have 3 events, urn 1, urn 2 and urn 3, and then this is your event A. Now probability of choosing urn 1, we choose urn 1 when both heads and tails are present. So we get 2 cases, either it will be this HT or TH. Now it will be this 2 by 9 plus 2 by 9, 4 by 9. So probability of choosing urn 1 will be 4 by 9. Now we'll get U2 when it is both heads, and if it is both heads, it will be HH. There will be 2 by 3 into 2 by 3, which again is 4 by 9. So probability of U2 is also 4 by 9, and this probability that both of them their tails will be simply 1 by 9. Now we'll find this conditional probability that if we have chosen urn 1, then we get all 3 different color balls. Now total number of balls in urn 1 is 6. So there will be 6 C3, and then we have 1 red, 1 white and 1 green. So there will be 2 C1 into 3 C1 into 1 C1. And this is 6, and here will be this 5 into 4,
which is 3 by 10. Then the same way, probability of A by U2. Now in U2 we have again 6 balls. So there will be 6C3. And then here we have 3C1, 2C1 and then 1C1, which again will be 3 by 10. And for this third one also, we'll get the same result. It is 6C3 and here we have 3C1, 1C1 and 2C1. Same combination. So it will again be 3 by 10. Now we need to find this probability of A. Now this probability of A will be this summation probability of A intersection UI, where I varies from 1 to 3, and will be this conditional probability of UI into probability of A upon UI. Now this is 4 by 9 into 3 by 10 plus 4 by 9 into 3 by 10 plus 1 by 9 into 3 by 10, which again is nothing but 3 by 10. And this is 30%. That means your option C is correct. Now the question is, an artillery target may either be at point 1 with the probability 8 by 9 or at point 2 with the probability 1 by 9. We have 21 shells each, of which can be fired either at point 1 or point 2. Now, each shell may hit the target independently of the other shell with probability 1 by 2. That's it. The number of shells must be fired at point 1 to hit the target with maximum probability is x. Then we need to find the value of x by 2. Now, once we fire any shell, we can direct it either at this first target or at this second target. Now, probability of choosing this first target, it is 8 by 9, and probability of choosing the second target is 1 by 9. Now, suppose out of these 21 shells, we have fired x at this first target and 21 minus x at this second target. Now, we need to maximize this probability of hitting the target. Now, probability of hitting the target as a function of x will be given by, now probability of choosing this first target is 8 by 9. So it will be this 8 by 9, and we have fired x shells onto this first target. So at least one of them must hit the target. So what we'll do is we'll do it with exclusion. So we'll take 1 minus, and none of these x, it hits the target. So it'll be this 1 minus 1 by 2 to the power x. Now in the same way for this target second, this probability is 1 by 9 and it is destroyed with the probability 1 minus 2 to the power 21 minus x. Now we need to find the value of x for which this probability is maximum. So what we'll do is we'll differentiate. So we'll find dp upon dx, and it'll be this 8 by 9 and it is minus 1 by 2 to the power x ln 2 plus 1 by 9 and it is minus 1 by 2 21 minus x ln 2 into minus 1. So it will be minus minus plus 1 and it should be equal to 0. Now if we put it equals to 0, this 1 by 9 log 2 will cancel. So we'll get this as 8 into 1 by 2 to the power x. It should be equal to 1 upon 2 to the power 21 minus x. Now this is 1 upon 2 to the power minus 3. So we can write 1 upon 2 to the power x minus 3 will be equal to 1 upon 2 to the power 21 minus x. Now if we compare, we'll get this as 2x equals 24. Value of x is 12. So out of these 21 shells, 12 must be directed at point 1 and 9 must be directed at point 2 to maximize this probability of hitting the target. And here we need to find the value of x by 2. So if x is 12, the value of x by 2 is 6, and that is the answer to this question. Now the question is, a die A has 2 white and 4 red faces, where die B has 4 white and 2 red faces. A coin is flipped once
If it shows heads, then game continues by throwing die A, and if it shows tail, then die B is used. If the probability that die A is used is 32 by 30, when it is given that red turns up every time in first n throws, find the value of n. Now first we toss a coin. Either we'll get a head or a tail. The probability of getting heads is 1 by 2 and probability of getting tail is 1 by 2. Now if it is a head, then we throw this die A. Now we throw die A, then red turns up every time in first n throws. So probability of getting red, it is 4 by 6 and there will be 2 by 3. So this probability will be 2 by 3 to the power n. And if it is tail, then we roll this die B which has 4 white and 2 red. Now getting all n reds is 1 by 3 to the power n. Now this is for die A and this is for die B. Now it is given that red turns up every time, then the probability that it is die A, it is a Bayes theorem question. So if it is Bayes theorem question, if it is red, then this is die A. So this case it will come in the numerator. So it will be this 1 by 2 and 2 by 3 to the power n divided by this total case which is 1 by 2, 2 upon 3 to the power n plus 1 by 2 into 1 upon 3 to the power n. It is 32 by 33. Now this 1 by 2 will cancel. Now we can write this as 2 to the power n upon 2 to the power n plus 1. So which is 2 to the power 5 upon 2 to the power 5 plus 1. So value of n is nothing but 5. So in this case, the value of n is 5 and that is the answer to this question. Now the question is, a set A has 22 elements and a subset P of A is selected at random. After replacing the elements, again a subset Q of A is selected. The probability that P and Q have exactly 5 elements in common is. Now here we know that number of elements in P intersection Q, it is 5. So first we have to choose which are the 5 elements which are common to both P and Q. So from these 22, we have to select any 5. So it will be 22C5. Now we are left with remaining 17 elements. And for each of these remaining 17 elements, we have 3 choices. Either each element may go to P or Q or neither P nor Q. So there will be this 3 to the power 17. Now for total number of cases, we have 22 elements and for each element we have 4 choices. Either it'll go in P alone or in Q alone or in both P and Q or in neither P nor Q. So there'll be simply 4, 4, 4, 22 times. So this value will be 22C5 3 to the power 17 upon 4 to the power 22. Now 22C5 is same as 22C17 and that's your option C. Now the question is, there are 17 railway stations on a railway track between A and B. The train stops at 4 intermediate stations at random. Find the probability that at least 2 of these 4 stations are consecutive. So what we'll do is, we'll do it with the exclusion. So we'll find this probability 1 minus and then no 2 stations are, probability that no 2 stations are consecutive. Now this probability will be 1 minus. Now total number of ways of choosing 4 stations, there will be 17C4. Now we have to find number of non-consecutive selection in a row. Now we have already studied that in one of the previous videos, how to find number of non-consecutive selections in a row or along a circle. Now if we have n arranged objects in a row and out of which we have to select k non-consecutive objects, it is given by n minus k plus 1 ck. So it will be this 17 minus 4 plus 1 c4. So this probability will be 1 minus 14c4 upon 17c4. Now this is 1 minus 14, 13, 12 and 11 and this is 17, 16, 15 and 14. Now 14 will cancel. Now this is 3 and 4 and this is 5. So this value is 1 minus 143 upon 340, which is 197 upon 340. Now the question is, a determinant is chosen at random from a set of all determinants of order 2 with elements 0 or 1. Find the probability that determinant chosen is negative. Now, in 2 cross 2 determinant, we have 4 positions, and for each position we have 2 choices. So there will be 2 to the power 4, that is 16 determinants possible altogether. Now, when we have all 4 zeros, so that's just one case, and in this case, determinant of this matrix will be 0. Now we have the second case when one of them is 1 and 3 of them 0, and this one, it can occur in any of these 4 positions. So we have 4 cases here. So if this was one case, and these are 4 cases. Now here also, determinant of A, it is 0. Now we have this third case when we have 2 ones and 2 zeros. Now if we arrange them together in one row or one column, we have 4 cases, and in these 4 cases, determinant of A will be 0, and then there will be these 2 cases when we have 1 0 0 1 and 0 1 1 0, where the determinant is non-zero. Now in this case, determinant is 1, and in this case, determinant is -1. We have 1 4 4 and these 2 cases. So altogether now we have 10 11 cases. Now fourth case is when 3 of them they are ones and 1 of them it is 0. So here we have 4 cases. Now in this, if 0 occurs along principal diagonal, then the determinant, it will be -1. So for the 2 cases, determinant is -1, and if 0 lie along this other diagonal 1 1 0 1, then determinant of A will be 1. So out of these 4 we have 2 choices here. So 2 here and 1 here. And then finally we have this final case when all the 4 they are ones. In that case also, determinant of A is 0. So this probability that determinant of A is less than 0 will be given by 3 by 16. And if the question is determinant of A greater than 0, so for greater than 0 we have this 1 case and 2 case here. So it will be this 3 by 16. And if we are supposed to find determinant of A equals to 0, then we have 9 and 1 10. So there will be 10 by 16. Now the question is, there are 4 boxes A1, A2, A3 and A4. Box AI has I cards, and on each card a number is printed. The numbers are from 1 to I. A box is selected randomly. The probability of selection of box AI is I by 10, and then a card is drawn. Now let EI represent the event that a card with number I is drawn. Now first one is, we need to find this probability of E1. Now probability of E1 is that card with number 1 is drawn. Now this card, it can come from any box. So it will be this PAI and then probability of E1 upon AI for I varies from 1 to 4. So it will be this summation I varies from 1 to 4. Now probability of choosing AI is simply I by 10, and probability of getting 1 from AI is simply 1 by I. So this probability is simply 1 by 10. So it will be 1 by 10, 1 by 10, 1 by 10 4 times. So there will be 4 by 10, which is 2 by 5, option C. Now the second part is, if the number chosen is 2, then find the probability that it has come from A3. Now probability of choosing E2 will be this summation. I varies from 1 to 4. Probability of choosing AI into probability of choosing E2 upon AI. Now, in the first box, there is only one card and which is 1. So we cannot get anything from this first box. So this first probability will be 0. So now we are left with this probability, that probability of A2, probability of E2 upon A2, probability of A3, probability of E2 upon A3, and probability of A4, probability of E2 upon A4. Now this is 2 by 10 into 1 by 2. This is 3 by 10 into 1 by 3. And this is 4 by 10 into 1 by 4. So this probability is 3 by 10. Now we need to find this probability that if the card is E2, it has come from this third box. So we'll take this case in the numerator. So it will be this 1 by 10 divided by 3 by 10, which is 1 by 3, and that's your option B. Now the next one is find the expectation of number on the card. Now number on the card, it could be either 1 or 2 or 3 or 4 and their corresponding probabilities. Now if the number is 1, this probability is 2 by 5 or simply 4 by 10. Now for E2, it is 3 by 10. Now for this number to be 3, it will be 2 by 10, and for 4, it will be simply 1 by 10. Now if we have to find mean of random variable Ex, which is mu, it will be this 4 by 10 plus 6 by 10 plus 6 by 10 plus 4 by 10, which is 2. So the expected value of the number on the cards is 2, and that's your option A. Now here the question is, two whole numbers are randomly selected and multiplied. The probability that units placed in their product is either 0 or 5. Now if we look at all the numbers, then the units placed will have either 0 or 1, 2, 3, 4, 5, 6, 7, 8 or 9. Now we have to choose two numbers. Now for each number, there are 10 possibilities for this unit digit. So total number of combinations will be simply 10 into 10. Now from this, we need to choose all the possible combinations where the product is either 0 or 5. Now first we look at all the condition when units digit is 0. It will be 0 if 0 gets multiplied with any other number. So it will be 0 into 1, 0 2, 0 9, or it could be 1 0, 2 0 up to 9 0, and then we can also have this 0 0. Now we have 18 plus 1, 19 cases. So it will be this 19 cases. We'll also get 0 when this 5 gets multiplied with an even number. Now 0 has been already considered, so it will be 5 2, 5 4, 5 6 and 5 8 into 2, because we can reverse the digits. So there will be 8 cases, and then finally we have this case where the units digit is 5. It is possible when this 5 gets multiplied with an odd number. So it will be 5 1, 5 3, 5 5, 5 7 and 5 9. Now except for 5 5, these 4 they can be reversed. So it will be this 8 plus 1, 9 cases. So total number of ways will be 19 plus 17, 36 by 100, which is 9 by 25, option C. Now here the question is, using the vertices of a polygon having 8 sides, a triangle is constructed at random. The probability that triangle so formed is such that no side of polygon is the side of triangle is. Now we need to find this probability. Now first, from these 8 points, number of triangles that can be formed is 8C3. Now what we'll do is, from the total, which is 8C3, we'll subtract all those triangles in which they have a side common with that of polygon. Now we have two cases. Case 1, when two sides are common. So if two sides are common, we have to select 3 consecutive vertices, and 3 consecutive vertices from the n cyclic vertices can be selected in simply n ways. So it can be done in only 8 ways. Now minus, and then in this case, when exactly one of the side is common, now we can select any one side in 8C1 ways. Now we cannot select these two. So that means from the remaining 4, we have to select any one, and that can be done in 4C1 ways. Now 8C3 is 8, 7, 6, and this is 3 into 2. So it will be this 56 minus 8 minus 32 upon 56, and which is 16 by 56. And this is 2 by 7. So this probability is 2 by 7, and that's your option 3. We can also solve this question using non-consecutive selection on a circle, for which I have already given a formula in one of the videos. You can refer to that video of non-consecutive selections. Now here the question is, 3 persons A, B and C in order cut a pack of cards, replacing them after each cut. The person who first cuts a spade shall win a prize. Find the probability that C wins the prize. Now any person who is going to cut a spade is going to win a prize. So the probability of winning a prize, it will be, now we have 13 spades and total we have 52 cards. So probability of cutting a spade is 1 by 4 and probability of not cutting a spade is 3 by 4. Now C is going to win if A doesn't win, B doesn't win, and then C wins, or A doesn't win, B doesn't win, C doesn't win, again A doesn't win, again B doesn't win, then C wins in the next trial, and this sequence will continue up to infinite. Now it is nothing but a GP. So this probability will be this Q square P upon 1 minus Q cube. So that is the required probability. Now Q is 3 by 4, so it will be this 9 by 16. P is 1 by 4, and here it is 1 minus Q cube, which is 27 by 64. So this probability will be 9 upon 64 minus 27, and which is 9 by 37, and that's your option 2. Now here the question is, A and B throw a pair of dice. A wins if he throws 6 before B throws 7, and B wins if he throws 7 before A throws 6. And if A begins, his chances of winning is. Now A is going to win if he throws 6, and we get 6 if we have 1 5, 2 4, 3 3, 4 2, and 5 1. So there will be this 5 by 36, and A not winning, it will be 31 by 36. Now in the same way, B is going to win if he or she throws 7. Now it will be 7 if it is 1 6, 2 5, 3 4, 4 3, 5 2, and 6 1. So this probability of B will be this 6 by 36, or simply 1 by 6, and B not winning is 5 by 6. Now we need to find the probability that A is going to win. Now A is going to win if A wins in the first chance, or if A doesn't win, B doesn't win, but A wins again in third chance, or A doesn't win, B doesn't win, again both of them, they don't win, and then A wins in the next chance, and this sequence will continue up to infinite. Now it is nothing but an infinite GP. So sum of this GP is PA upon 1 minus PA naught into P B naught. Now probability of A is 5 by 36. Now this is
Now PA0 is 31 by 36 and PB is 5 by 6. Now this probability is 5 by 36 and here it is 36 into 6 minus 31 into 5 upon 6 into 36. Now 36 will cancel. Now this is 30 upon 61 and that's your option 2.
Now here the question is 6 letters are written by a person to his 6 friends. The address of each friend is written on 6 envelopes. Letters are put in the addressed envelopes at random. Then find the probability that no letter goes into correct envelope. Now this is nothing but this is D6, that is de-arrangement of 6. Now this is factorial 6, 1 minus 1 upon factorial 1 plus 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4 minus 1 upon factorial 5 plus 1 upon factorial 6. Now it'll cancel. Now factorial 6 is 720. Now 720 divided by 2, 360. 360 divided by 3, 120. 120 divided by 4, 30. 30 divided by 5, 6. And this is plus 1. So this value is 391 minus 126 and which is 265. So this required probability is 265 and total number of ways of distributing these 6 letters in 6 envelopes, it is factorial 6 which is 720. So it will be this 265 upon 720. Now this is 53 and here it is 144 and that's your option B. Now the next one is the probability that exactly 2 letters go into correct envelopes. Now which 2? So from these 6 we have to select these 2. So it will be 6C2 into derangement of 4 letters. D4 divided by total which is factorial 6. Now 6C2 is 15 and D4 is factorial 4, 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4. Now this is 24 by 2, 12. 12 divided by 3, 4 and plus 1. So this is 9. So it will be 15 into 9 divided by 6, 5, 4, 3 and 2. Now this is 15. Now this is 3 and this is 2. So this value will be simply 3 by 16 and that's your option A. Now the next one is the probability that at least 2 letters go into wrong envelopes. Now for this third one, at least 2. This probability will be 1 minus either probability that no letter is in wrong one or exactly 1 letter is in the wrong envelope. Now this is a 1 minus. Now if all the letters are in correct envelope, then this probability is 1 by factorial 6 which is 720. Now if you look at this probability that exactly one of them is in wrong envelope. Now once we have 1, 2, 3, 4, 5, 6 and here it is 1, 2, 3, 4, 5, 6. Now it means that exactly one is in wrong, then other 5 they have to be in the same correct position. Now if 5 of them are in correct position, then the 6th one it cannot be in the wrong position. So this probability is actually 0. So the required probability is 719 upon 720 and that's your option D. Now the question is 16 players S1, S2 up to S16 play in a tournament. They're divided into 8 pairs at random. From each pair, a winner is decided on the basis of game played between 2 players of the pair. Assume that all players are of equal strength. Find the probability that exactly one of the 2 players S1 and S2 is among the 8 winners is. Now first we'll find total number of possible combinations. So total number of possible combinations is given by total number of pairs that can be made from these 16 pairs. So we have 16 pairs and we have to make pairs of 2, 2 and 2 8 times. So that will be factorial 16 upon factorial 2 to the power 8 into factorial 8. So that is our total number of cases. Now, for the favorable case when exactly one of the two players is among the 8 winners, we have to consider two possibilities. First possibility is when S1 is paired against S2. Now, if S1 and S2 they are paired against each other, then exactly one of them will be a winner. That means we have to distribute remaining 14 players in the pairs of 2 and 2. So there will be factorial 14 upon factorial 2 to the power 7 and factorial 7. And the second case, when S1 and S2 they are not paired against each other, and such pairs will be this total possibilities, which is 16 2 to the power 8 factorial 8 minus factorial 14 2 to the power 7 factorial 7. Now we have two pairs, suppose S1 and Si and then S2 and Sk. Now we need to find the probability that exactly one of them wins. Now probability of S1 winning, it is 1 by 2, and probability of S2 losing is 1 by 2. So we have two cases, either S1 is going to win and S2 is going to lose, or S2 is going to win and S1 is going to lose. So this is the favorable number of case in this second case. Now we'll calculate this required probability. Now this required probability will be this favorable cases factorial 14 2 to the power 7 factorial 7 upon factorial 16 2 to the power 8 factorial 8 plus factorial 16 2 to the power 8 factorial 8 minus factorial 14 2 to the power 7 factorial 7 upon factorial 16 2 to the power 8 factorial 8 into 1 by 2. Now first we'll calculate this probability. Now this is factorial 14 2 to the power 7 factorial 7, and this is factorial 16 2 to the power 8 and factorial 8. Now this is 2, this is 8, and here will be this 16 into 15. Now this is 1 by 15. So this probability is simply 1 by 15. So we can write this as 1 by 15. Now this is 1 minus 1 by 15 into 1 by 2. So this is 1 by 15 and this is 7 by 15. So the required probability is simply 8 by 15, and that's your option C. Now it says 6 faces of a die are marked with numbers 1, -1, 0, -2, +2 and 3, and the die is thrown thrice. The probability that sum of the numbers thrown is 6 is. Now we have thrown this die thrice and we have to find the combination such that sum of numbers is 6. So we'll get 6 when we have 3, 3 and 0. We can also get 6 when we have 2, 2 and 2, or it could be 3, 2 and 1, and there is no other combination possible. Now for this first one, it should be 3, 3 and 0, and this 0, it can occur at any one place, so it will be this 3C1. Now probability of choosing 3 will be 1 by 6, and then again it will be this 1 by 6, and probability of choosing 0 will be this 1 by 6. Now here it will be all 2's, which is 1 by 6 into 1 by 6 into 1 by 6, and here it will be this 3, 2, 1, and which is possible in factorial 3 ways, and again it will be this 1 by 6 into 1 by 6 into 1 by 6. So this required probability will be 3 plus 1, 4, 4 plus factorial 3, 10, 10 by 216, and that's your option 3. Now here the question is the probability that in a group of n people, at least 2 of them will have the same date of birth of a non-leap year, assuming a year to have 135 days. So this required probability we have to find out using its complement. So what we'll do is we'll find 1 minus and the probability that none of them, they have the same date of birth. Now for these n people each, we have 365 possibilities. So total number of possible combinations will be 365 to the power n. Now for each of these n people, we must select n possible dates, and it can be done in 365 p n ways. So this required probability is 1 minus 365 p n upon 365 to the power n, and that's your option 1. Now here the question is, consider the experiment of distribution of balls among urns. Suppose we are given m urns numbered from 1 to m, among which we are to distribute n balls which is less than m. Let PA denote the probability that each of the urns numbered 1 to n will contain exactly one ball. Then answer the following. If the balls are different and any number of balls can go into any number of urns, then PA is equal to what? Now PA is when the urn from 1 to n will contain exactly one ball. Now first we'll find total number of possible cases. Now for each ball, we have m choices. It can go to any of these m urns. Now for the first ball, we have m choice. For the second ball also, we have m choice. So for all the n balls, we have m choices each. So total number of possible combinations will be simply m to the power n. Now for this event A to occur, n balls must go into n urns. So basically it is a bijection between the two sets. So these n balls can be distributed in n urns in factorial n ways, and the required probability is factorial n upon m to the power n, and that's your option B. Now the second one is, if the balls are identical and any number of balls can go to any urn, then this PA is equal to what? Now first we have to distribute these n balls in m distinct urns. Now this is x1 plus x2 plus xm, and it must be equal to n, where x1 is number of balls in first urn, x2 is number of balls in second urn, and xm is number of balls in nth urn, and it should be n. And we have to find number of non-negative integral solutions of this equation. And we know that number of non-negative integral solution is given by m plus n minus 1 c m minus 1. So total number of cases will be m plus n minus 1 c m minus 1. Now the favorable case is PA when each of the urn numbered from 1 to n gets one ball each. Now since all the balls are identical, there is only one way in which we can distribute one ball each to first n urns. So this required probability will be 1 upon m plus n minus 1 cm minus 1, and that's your option B. Now it says, if the balls are identical but at most one ball can be put in any box, then PA is equal to what? Now if only one ball can be put into one box, then total number of ways of distributing these balls will be, now from these m urns, we have to choose any n urns which can be done in MC n ways. And once we have chosen n urns, then these balls, they can be distributed in only one way because the balls are identical. Now again PA, n balls are put into first n urns, so it will be simply 1. So this required probability will be 1 upon MCN, and that's your option D. Now here the question is, a set A contains 10 elements. A subset E of A is selected at random, and after noting all the elements, they are replaced. Again a subset F of A is selected at random. Now first one is, find the probability that E and F have no common elements. Now first is total number of ways of selecting these two subsets E and F. Now for each element we have 4 choices. Either it will belong to E only, or it will belong to F, or it will belong to E intersection F, or it doesn't lie in E and it doesn't lie in F. So total number of ways of choosing these two subsets E and F, it is given by 4 to the power 10. Now when E and F have no common elements, then for each element we now have only 3 choices. So there will be simply 3 to the power 10. So this required probability is 3 to the power 10 upon 4 to the power 10, and that's your option D. Now the next one is probability that E and F have equal number of elements.
Now suppose they have, now for this again, total number of choices will be 4 to the power 10. Now they have equal number of elements. The first possibility is both of them, they are null set. So in that case, we have to choose 10C0 and 10C0. So it will be this 10C0 square. Now one element in E and one in F. Now one in E is 10C1 and one in F is also 10C1. So it will be this 10C1 square, and it'll continue and it'll go all the way up to 10C10 whole square. Now we know that NC0 square plus NC1 square up to NCN square, it is given by 2NCN. So it will be this 20C10 upon 4 to the power 10, and that's your option A. Now the third one is probability that E and F have exactly 3 elements in common. Now which 3? We have to select these 3 elements. So it will be this 10C3. Now for the remaining 7 elements, we have 3 choices, either E or F or neither E nor F. So there will be 3 to the power 7 whole divided by 4 to the power 10. Now 10C3 is 10, 9, 8 into 3 to the power 7, and this is 3, 2 and 4 to the power 10. Now this is 3, this is 4. Now we'll take it here and we'll divide 4, so it will be this 4 to the power 9. So we can write this as 10 into 3 to the power 8 upon 4 to the power 9, and that's your option B. Now the question is, a point PXY is selected at random inside the square with boundaries x equals 0, y equals 0, x equal to 4 and y equals 4. So we have our coordinate axis, and then we choose this square of length 4 units. So this is 0, 0, 4, 0, 0, 4 and 4, 4. Now this is a question of geometrical probabilities. So the area corresponding to this entire subset will be equal to area of the square, which is 16. Now we need to find the probability that the point P is inside the parabola y square equals x. Now y square equals x. Now when x is 4, y is 2. So it will be this parabola y square equals x, and we have to find the probability that this point lies in this area. So number of elements in this set, it is equivalent to area of this curve from 0 to 4. So we can write this as this integral from 0 to 4 and then y dx. Now this is from 0 to 4 under root x dx. So it will be this x to the power 3 by 2, and this is 2 by 3 from 0 to 4. Now this is 2 cube. So it will be this 16 by 3. So now this required probability is favorable area 16 by 3 upon total area, which is 16. So it will be this 1 by 3, or we can write this as 3 by 9. So the value of k is simply 3. And that is the answer to this question. Now the question is, there are 2 red, 2 blue, 2 white and a certain number greater than 0 of green socks in a drawer. If 2 socks are taken at random from the drawer without replacement, the probability that they are of the same color is 1 by 5, then number of green socks are. Now suppose number of green socks is n. Total number of socks we have is 2 plus 2 plus 2, 6, 6 plus n is n plus 6, and from n plus 6, we have to select any 2. Now favorable cases, when both of them they have the same color, so it could be either 2 red, so it will be this 2C2, or 2 blue, or 2 white, or 2 green, and this probability is 1 by 5. Now this is 3 plus n minus 1 by 2, and here it is n plus 6 into n plus 5 divided by 2, and this is 1 by 5. Now this is 6 and 5 into 6 is 30 plus 5 n square minus 5n, and it will be equal to n square
plus 11n plus 30. Now 30 will cancel. We can write this as 4n square minus 16n equals 0. So value of n here is simply 4. And that is the answer to this question. Now the question is, a number A is randomly selected from the set from 0 to 99. The number B is selected from the same set. The probability that number 3 to the power A plus 7 to the power B has a digit equal to 8 at its unit place. Now if we look at powers of 3, 3 to the power 0 is 1. 3 to the power 1 has 3 in the units place. 3 square has 9. 3 cube has 27. And 3 to the power 4 is 1. So these values, they are going to repeat after every 4 powers. Then the same way we look at powers of 7. 7 to the power 0 is 1. 7 to the power 1 is 7. 7 square has 9 in the units place. 7 cube has 3. And 7 to the power 4 has 1. Again, we'll have these values repeated after every 4 power. Now it says we need to find the probability that the number has digit equal to 8 in the units place. Now we'll get 8 in the units place if we choose 1 here, and then correspondingly we have 7 here. If we choose 9 here and we take 9 from this, or if we choose 7 from this and we choose 1 from this. Now if we look at values of A, then out of these 100, we have 25 sets of 1, 3, 9 and 7 each. So probability of choosing this favorable A will be simply 3 divided by 4. And once we have chosen A, then B is automatically chosen 1 out of 4. So it will be this 1 by 4. So the required probability is 3 by 16, and that's your option D. Now the question is, for any two events A and B, which of the following is true? Now the first one is P A by B. Now we know that PA by B is PA intersection B upon probability of B. We are given that probability of B is unequal to 0. Now we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B upon probability of B. Now maximum value of A union B is 1. So it will always be greater than or equal to probability of A plus probability of B minus 1 upon probability of B. That means this option A, it is correct. Now if we look at this option B, it is probability of A intersection B naught. Now probability of A intersection B naught, it is clearly probability of A minus probability of A intersection B, because it is that part of A which doesn't contain B. So there will be probability of A minus probability of A intersection B. So option B is also correct. Now if A and B are independent, then we can write probability of A union B as 1 minus probability of A union B complement, and this is 1 minus probability of A complement intersection B complement, and we can write this as 1 minus probability of A complement into probability of B complement. That means option C is also correct. Now what about option D? If A and B are disjoint, then we can write probability of A union B as probability of A plus probability of B minus probability of A intersection B, which in this case will be 0. So it will be simply this PA plus PB, and we cannot write it in this form. So the correct options are A, B and C. And the third question is, two different numbers are taken from the set 0, 1, 2, 3 up to 10. The probability that their sum and positive difference are both multiple of 4 is x by 55. Now two different numbers, it can be taken in 11C two ways, which is 55. Now we have to find two different numbers such that their sum and their difference, it is both multiple of 4. Now sum and difference, they are both multiple of 4 if both of them they are either even or both of them they are either odd. Now one of the possibilities 04, 08, and then we'll have 26 and 210. Then we have 48 and 610 is 4, but 5 plus 1 is not a multiple of 4. Now 7 plus 1 is a multiple of 4, but 7 minus 1 is not a multiple of 4. And the same way 9 minus 1 is 9 plus 1 is not. And if we look at 7 and 3, sum is not multiple of 4. 9 minus 3 is not a multiple of 4. 5 and 9, sum is not a multiple of 4. So we do not have any option for odd numbers. So this required probability is this 6 upon n, which is 6 by 55. So here the value of x is simply 6. Now here the question is, a coin has probability p of showing heads when tossed. When it is tossed n times, let Pn denote the probability that no two or more consecutive heads occur. Then which of the following is true? Now if we toss a coin once, then two heads can never appear. That means this probability 1 is going to be always 1. So this A, it matches with R. Now if we consider P2, in P2 we have two coins tossed. Now we need to find the probability that no two or more consecutive heads occur. Now what we'll do is, in order to find P2, we'll subtract from 1 the case when both of them are heads. Now probability of getting a heads, it is P. So it will be this P into P. So this P2 will be 1 minus P square. So this B, it matches with Q. Now before this third one, we'll take this fourth case when we have Pn. That is, we have tossed n coins. Now suppose we have tossed these n coins. And Pn is the probability that no two or more consecutive heads occur. Now we'll consider two cases. Case 1, when this nth coin shows a heads, or when this nth coin shows a tails. Now if the nth coin shows a tails, then for the previous n minus 1 coins, there should be no consecutive heads. So we can write this Pn, if it is tails, now probability of getting a tails is 1 minus P into probability of no consecutive heads in n minus 1 coins. But if it is heads here, then here it must be tails. Otherwise we'll have two consecutive heads. And if these two are decided, then it can be any configuration in n minus 2 coins. Then it will be this heads, which is P, tails, which is 1 minus P, and then it will be P n minus 2. That means this D, it matches with S. Now once you have this general formula, we can write P3. Now P3 is going to be 1 minus P into P2 plus P into 1 minus P into P1. Now P1 is 1 and P2 is 1 minus P square. So we can write this as 1 minus P, and here it will be 1 minus P square plus P. Now if we simplify this, we can write this as 1 minus P square plus P minus P plus P cube minus P square. Now P and P will cancel, so this probability will be 1 minus 2P square plus P cube, and that's your option P. So this C, it matches with P. And this is the answer to this question. Here the question is, 12 identical coins are distributed among 3 children at random. The probability of distributing so that each child gets at least 2 coins is k by 13, then find the value of k. Now first we'll find total number of ways of distributing 12 identical coins in 3 children. Now suppose the first child gets x1, second gets x2, and third child he gets x3. So total we have 12 coins, and each of xi should be greater than or equal to 0. We have to find number of non-negative integral solutions. So total number of cases, it will be n plus r minus 1 c r minus 1, and that will be 14c2, and 14c2 is 7 into 13. Now we need to find favorable number of cases.
Now we have this favorable number of case when each child gets at least 2 coins. Now if each child gets at least 2 coins, what we'll do is we'll replace this xi with xi dash and we'll write xi dash as xi plus 2. So here xi dash will be greater than or equal to 0. Now we replace each of them, it will be this x1 dash plus x2 dash plus x3 dash and they'll be equal to 6. Now we need to find number of non-negative integral solutions. So total number of favorable cases will be 6 plus 3 minus 1 C, 3 minus 1 and there will be 8 C2 and 8 C2 is 4 into 7. Now we need to find this required probability. So this required probability is favorable case which is 4 by 7 upon 7 by 13. So it will be this 7 by 13. So this 7 will cancel. So this probability is 4 by 13 and it is given in the form k by 13. So clearly value of k is 4 in this case. Now here the question is a purse contains 2 coins of which one is a two-headed coin and the other one is a fair coin. A person selects one of the coins at random and tosses. If he gets heads, he tosses the other coin. Otherwise, he tosses the same coin. It is given that he got head in the second toss. Find the probability that this first selection is a fair coin and getting heads is which of the following. Now, a purse contains 2 coins. One of them is fair coin and the other one is two-headed coin. Now, probability of choosing a fair coin, it is 1 by 2 and probability of choosing a two-headed coin is 1 by 2. Now, if a fair coin is tossed, we get 2 outcomes. Either it will be this heads or tails. We'll get heads with the probability 1 by 2 and tails with the probability 1 by 2. Now, if it is heads, he tosses the other coin. So, in this case, if the first coin is fair, he's going to toss this two-headed coin. And in this case, probability of getting a heads, it is simply 1. Now, if it is tails, he tosses the same coin. So, if it is tails, then again it could be either heads or tails, which again is 1 by 2 and 1 by 2. Now, if he has chosen this two-headed coin, he's going to toss. He'll get this heads. And once he gets heads, he has to toss now a fair coin, which can result in either heads or tails. So, it will be this 1 by 2 and 1 by 2. Now, it says, it is given that he got heads in the second toss. Now, we need to find this probability that first selection is a fair coin and getting heads. So, that means first coin, it should be fair and we should get a head. So, this case, it should be in the numerator and all other cases will be in the denominator. So, this required probability will be this 1 by 2 into 1 by 2 into 1 upon, now this is 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2 into 1 by 2 and plus this case which is 1 by 2 into 1 into 1 by 2. So 1 by 2 into 1 into 1 by 2. Now we divide everything with 1 by 4, we get 1 and this is 1 plus 1 by 2 plus 1. So this probability will be simply 2 by 5 and that's your option C. Now the question is, a student appears for tests 1, 2 and 3. A student is successful if he passes either in test 1 and 2 or tests 1 and 3. The probability of student passing in tests 1, 2 and 3 are P, Q and 1 by 2. If the probability that student is successful is 1 by 2, then which of the following is correct? Now the student will be successful if he passes in first and second and doesn't pass his third, or he passes first, doesn't pass second, but he passes third, or he passes all the 3 tests. Now all these probabilities, they are independent. So for the first one, passing the first, it is P, passing the second, it is Q, and not passing third is 1 by 2. Now for this one, this is P, not passing second is 1 minus Q, and then it is 1 by 2, or passing in all 3. So it will be this PQ 1 by 2, and it is given that this probability is 1 by 2. Now here this 1 by 2 will get cancelled. So we can write this as P plus PQ, it is equal to 1, or P into 1 plus q, it should be 1. Now, what are the possibilities? If we put p as 1, q as 0, it is satisfied. Now, if we put p as 2 by 3 and q as 1 by 2, so this 1 by 2 will be 3 by 2, this again will be 1, so b is also satisfied. If we put p as 3 by 5, so it will be this 3 by 5 and 1 plus q is 5 by 3. This is also true. And if we look at this, this is nothing but rectangular hyperbola. So there will be infinitely many possible values of p and q. So all the 4 options, they are correct. Now the question is, an unbiased coin is tossed n times and let x denote number of times head occurs. If p x equal to 4, x equal to 5 and x equal to 6 are in AP, then the value of n can be. Now p x equal to 4 is nc4, p to the power 4, q to the power n minus 4. This is nc5, p to the power 5, q to the power n minus 5, and this is nc6, p to the power 6 and q to the power n minus 6, and it says they are in AP, where p is 1 by 2 and q is 1 by 2. Now since p and q, they are all 1 by 2, so this factor in all the 3 cases will be 1 by 2 to the power n. So we can simply write 2nc5 1 by 2 to the power n equals nc4 1 by 2 to the power n plus nc6 1 by 2 to the power n. Now 1 by 2 to the power n will cancel. Now what we'll do is we'll divide everything with nc5. So this is 2 and this is nc4 upon nc5 plus nc6 upon nc5. Now n is same, r differs by 1, so we can write this as n minus r plus 1 upon r, and here also will be n minus r plus 1 upon r. So it will be this 2 and then 5 n minus 4 plus n minus 5 by 6. Now if we simplify this, we can write this as 12n minus 48 will be this 30 plus n square minus 9n plus 20. So it will be this n square minus 21n plus 98 equals 0. Now this is 14 into 7 and 14 plus 7. So if we solve this, we'll get value of n as either 7 or 14. And that's your options A and D.
Now here the question is, if P and Q are chosen randomly from the set 1, 2, 3 up to 10 with replacement, then the probability that roots of this equation are real, imaginary, real and equal, and real and distinct is. Now discriminant for this quadratic equation will be P square minus 4Q. Now if we consider this first case when discriminant is equal to 0, that is when the roots are real and equal, in that case we'll have P square equals 4Q, or we'll get P as 2 under root Q. Now in this, Q has to be a perfect square. So in this case, the values of Q which are possible is Q can be 1, Q can be 4 and Q can be 9. Now if we take Q as 1, we get P as 2. If we take Q as 4, we'll get P as 4. And if we take Q as 9, we'll get P as 6. So these are the 3 cases possible. So this required probability that they are real and equal will be this 3 divided by total number of ways. Now for P we have 10 choices and for Q we have 10 choices. So that will be this 3 by 100, and that's your option C. Now if we take the second case when D is greater than 0, which means this P square minus 4Q should be greater than 0 or Q is less than P square by 4. Now what are the possible options for P and Q? Now if P is 1, Q is less than 1 by 4, no option. If P is 2, Q is less than 1, again no option. So the smallest one will be P equals 3. Now if P is 3, Q is less than 9 by 4, and 9 by 4 is 2 point something. So value of Q is either 1 or 2. So we have 2 cases here. Now if P is 4, now it will be the 16 by 4 is 4. So the Q can take the values 1, 2 and 3. So there will be 3 cases here. If we take P as 5, now 25 divided by 4, there will be 6 point something. So Q can take the value from 1 to 6. So we have 6 phase. If P is 6, there will be Q is less than 9. So you take the value from 1 to 8. If P is 7, there will be 49 by 4 is 12 point something. So here you can take values from 1 to 10. So for all the values of P from 7, 8, 9 and 10, you can take all these 10 values. So here for these 4 cases, total values we have is 40. Now if we add them, we'll get this as 59. So the probability that roots are real and distinct will be this 59 by 100. That means option D is incorrect. Now roots are real when they are either real and equal or real and distinct. So this probability that roots are real will be this 59 plus 3, which is 62. 62 divided by 100, and that will be 31 by 50. So this option A, it is incorrect. Now they will be imaginary if they are non-real. So it will be 1 minus 31 by 50, and that will be 19 by 50. That means option B is correct. So the correct options are B and C. Now here the question is, out of 2n plus 1 tickets consecutively numbered, 3 are drawn at random. The chances that the numbers are in AP is. Now if we find total number of ways of choosing 3 tickets, it will be 2n plus 1 C3, and these 3 tickets, they are in AP, and for this AP we have worked out a formula which I have discussed in the compendium, and the formula is, it is n minus 1 whole square by 4 if n is odd, and it is n into n minus 2 by 4 if n is an even number. Now in this case we have odd number of tickets, so here this favorable case will be 2n plus 1 minus 1 whole square upon 4. So it will be simply this n square. So this required probability will be n square upon 2n plus 1 C3. Now this is n square, and this is 2n plus 1 into 2n minus 1, and here it is 6. Now this n will cancel, it will be this 3. So we can write this as 3n upon 4 n square minus 1, and there will be a option 3. Now it says there are 6 red balls and 6 green balls in a bag. 5 balls are drawn out at random and placed in a red box. Remaining 7 balls are put in a green box. If the probability that number of red balls in green box plus the number of green balls in the red box is not a prime number is P by Q, where P and Q are relatively prime, find the value of P plus Q. So initially we have 6 red and 6 green balls. Now from this we have drawn 5 balls, and we have put those 5 balls in the red box, and then remaining 7 balls, they are put in green box. Now it says if the probability that number of red balls in green box, so suppose number of red balls in green box is R and number of green balls in red box is G. So in red box we have G green and 5 minus G red, whereas in green box we have R red and 7 minus R green balls. Now if we count total number of red balls, it will be 5 minus G plus R, and it will be equal to 6, and total number of green balls, there will be G plus 7 minus R, and it should be equal to 6. So from here we can write value of R minus G, it should be 1. So that is the relationship between R and G. Now it is also given that R plus G, it is not a prime number. Now we need to find possible values of R and G. Now clearly G must be less than or equal to 5 and greater than 0, and R must be less than or equal to 7 and it must be greater than 0. Now we look at various combinations of R and G. Now R could be 1 and G could be 0. Now in this case R minus G is 1 and R plus G is not a prime number, so we're going to select it. It could be 2, 1 and 2 plus 1 is 3. We are not going to accept it. Now 3, 2, it is also prime. 4, 3, also prime. 5 plus 4, 9, it is possible. And then 6, 5. 6 plus 5 is 11. So out of these 6 cases, there are only 2 cases where this R plus G, it is not a prime number. Now we need to find this probability and it is given as P by Q. Now for this red, we need to choose 5 balls. So out of 12, we can choose any 5. So it will be 12C5. And the first case, we have 1 red and 0 green. So from this, it will be 6C1 into 6C0 plus here it is 6C5 into 6C4. So this probability will be 6 plus 6 into 15 upon 12, 11, 10, 9, 8, 5, 4, 3, 2, 1. Now 4 into 3 is 12, 5 into 2 is 10. Now this value is 6 into 16 upon 11 into 9 into 8. Now this is 2. So it will be this 12 upon 99, which is 4 by 33. So in this case, value of P is 4 and value of Q is 33. Now we need to find the value of P plus Q. Now P plus Q in this case is 37 and that is the answer to this question. Now here the question is, a mapping is selected at random from a set of all mappings of the set A 1, 2, 3, 4 to itself. The probability that mapping selected is a bijection. Now total number of mapping. For each element we have 4 choices. So there will be 4 into 4 into 4, 4 times. So it will be 4 to the power 4. Now if it is a bijection, then it will be a 1, 1 function. So we have to arrange these 4 against the permutations of these 4, and which is done in factorial 4 ways. So this probability is factorial 4 upon 4 to the power 4 or factorial 3 upon 4 cube, and that's your option 3. Now here the question is, indicate the correct order sequence in respect of the following. Now the first one is, if the probability that a computer will fail during the first hour of operation is 0.01, then if we turn on 100 computers, exactly 1 will fail in the first hour of operation. Now we are given that value of P is 0.01, value of N is 100. Now P x equal to 1, it is given by 100C1, P to the power 1 and Q to the power 99, and it is not equal to 0.01. So that means this first one, it is false. Now what about the second one? Now second one, it says a man has 10 keys, only one of which fits the lock. He tries them in a door one by one, discarding the one he has tried. Now we need to find the probability that fifth key fits the lock is 1 by 10. Now first one, it should be a failure, so it will be this 9 by 10. Second one, it will be 8 by 9. Third one, 7 by 8. Fourth one, 6 by 7. Now this fifth one has to be the right key, so it will be then 1 by 6. So this probability will now be 1 by 10. That means this second one, it is true. Now this third one is, given that events A and B such that PA equals 1, then A and B are independent. Now we know that if PA equals 1, then B is a subset of A, then probability of A intersection B, it will be equal to probability of B. Now we can also write this as probability of A intersection B into probability of B into 1, and this 1 is nothing but probability of A. So we can write this as probability of B into probability of A. So that means this third one is also true. Now the fourth part is, when a fair six-sided die is tossed on a tabletop, the bottom face cannot be seen. The probability that product of number on the 5 faces that can be seen is divisible by 6 is 1. Now, if the bottom face, which is not visible, it is 6, then too we have 3 into 2 in the product. That means this product will always be divisible by 6. And if it is not 6, then in that case, it will have 6 on one of the face. Therefore, this product will again be a multiple of 6. So it is true for any case. So this probability will always be 1. So that means this fourth option is also true. So answer to this question is false, true, true, true. And that's your option B. Now here the question is, a clerk was asked to mail 4 report cards to 4 students. He addresses 4 envelopes that unfortunately paid no attention to which report card be put in which envelope. What is the probability that exactly one of the students receive his or her own card? Now out of these 4, one of them has received the correct card. It can be done in 4C 1 ways. Now for the remaining 3, there has to be D arrangement. So they'll be equal to D3, and total number of ways in which 4 cards can be put into 4 envelopes, it is factorial 4, and this is the required probability. Now 4C1 is 4 and D3 is nothing but 2, and this probability is simply 1 by 3, and that is the answer to this question. Now here the question is, 2 cubes have their faces painted either red or blue. Now first cube has 5 red faces and 1 blue face, and the second cube, it has, suppose, R red faces and 6 minus R blue faces. Now it says, when the 2 cubes are rolled simultaneously, the probability that 2 top faces show the same color is 1 by 2. So either both the faces they'll be red, or both of them they'll be blue. Now probability that they'll be red, it is given by 5 by 6 into R by 6 plus both blue, 1 by 6 into 6 minus R by 6, and it is given that it is equal to 1 by 2. Now this is 5R minus R, there will be 4R. So 4R plus 6 will be equal to 18, or 4R equals 12. Value of R is simply 3. So on the second cube there are 3 red faces, and that's your option C.
Now here we have a matching question, and it says, in a tournament there are 16 players, S1, S2, S3 up to S16, and they're divided into 8 pairs at random. From each game, a winner is decided on the basis of game played between the 2 players of the pair. Now assuming that all the players have equal strength, first one is, we need to find the probability that S1 is one of the winners. Now in the first phase, we have divided the 16 players in 8 random pairs. Now this S1 will be paired with randomly against any player Si, where I varies from 2 to 16. Now S1 is going to be among the winners if S1 wins his or her match against Si, and probability of S1 winning against Si, it is 1 by 2. So clearly this probability of S1 is one of the winners, it is 1 by 2. So this A, it matches with Q. Now B is the probability that exactly one of S1 or S2 is a winner. Now in the second case, we have 2 scenarios. Scenario 1 is if S1 and S2 they are paired against each other, or this case where they are not paired against each other. Now if we look at this first case when S1 and S2 they are paired opposite each other, then if we take S1, then there are 15 possible pairing combinations for S1, and from these 15 we get S1 S2 if we have S2 as an opponent. So this probability will be simply 1 by 15. Now in this case, probability of winning exactly one of them, it is simply 1. Now if we take the second case when they are not paired against each other, it will be this 1 minus 1 by 15. Now in this we have two possibilities, when S1 wins and S2 loses, or S2 wins and S1 loses. So it will be this 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2. So this probability will be 1 by 15 plus 14 by 15 into, now this is 1 by 2. So this is simply 8 by 15. So this B, it matches with B. Now this third case is both S1 and S2 are among 8 winners. Now they cannot be among 8 winners if they are paired opposite each other. So that means in this third case it is clear that S1 and S2, they must not be paired against each other. Now this probability that they are not paired against each other, it is 1 minus 1 by 15 into, now S1 must win, so it will be this 1 by 2, and S2 must also win, it will be 1 by 2. So this probability will be 14 by 15 into 1 by 4, which is 7 by 30. So this C, it matches with R. And finally, when we have this D, which is both S1 and S2 are not among winners. So in this case also, they cannot be paired against each other. So for this fourth one, again we have S1 and S2 not playing against each other. So this probability will be 1 minus 1 by 15. Now in its pair, S1 must not win and S2 must also not win. Now this probability is same as that of third. So this again will be 7 by 30. So this D, it also matches with R. Now here the question is, a die is weighted such that probability of rolling the face numbered n is proportional to n square. Now this die is rolled twice, yielding the numbers A and B. Find the probability that A is less than B and this probability is P. Then find the value of graded function of 2 upon P. Now probability of getting any number n, it is proportional to n square. Now suppose this constant of proportionality is k. So we know that summation Pn, where n varies from 1 to 6. So it will be this summation k n square, where n varies from 1 to 6, it will be 1. Now this is k and this is n plus 1, 2n plus 1 divided by 6, and it is equal to 1. So the value of k is 1 by 91. So this probability of getting n on any dice, it is n square by 91. Now it says a die is rolled twice, yielding the numbers A and B. The probability that A is less than B is. Now if A is less than B, then the possible combination that we have here is 1, 2, 1, 3 up to 1, 6, and here will be this 2, 3, 2, 4 up to 2, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and then 5, 6. So these are the all favorable conditions for A and B such that A is less than B. Now we'll start writing this probability P. Now this probability P will be, now in each we get this 91. So it will be this 1 by 91 into 1 by 91, and then for 1 into 2, it will be this 1 square into 2 square. So there will be this 4. Then 1 square into 3 square, 9, 16, 25 and 36. Plus, now here we have 2 square, which is 4. And then 3 square plus 4 square, 5 square and 6 square. So there will be 9, 16, 25 and 36. Plus, now here we have 3. So it will be this 9 and then 16 plus 25 plus 36. And then we have the 16, which is 5 square plus 36. And then finally it will be this 25 into, and the 6 square is 36. Now this value will be 3003 upon 91 into 91. Now it says find the value of greatest interior function of 2 upon p. So we need to find greatest interior function of 2 by p. Now it will be this 2 into 91 into 91 divided by 3003. Now 91 divides 3003, and that will be this 33. Now 2 into 91 divided by 33, that will be 5.5 something. So greater function of this will be simply 5. So answer to this question is 5.
Now here the question is, let S be the sample space of random experiment of throwing simultaneously 2 unbiased dice with 6 faces numbered from 1 to 6. Let EK be the set AB such that A into B is K for K greater than 1. And if PK is probability of EK where K is greater than or equal to 1, then the correct among the following is. Now if we look at this P1, and P1 is basically this probability of E1, and E1 is when product of both the numbers is 1. So this is only one case, and that is 1, 1. So this probability is simply 1 by 36. Now if we look at P30, P30 is probability that this product is 30. We get this product as 30 if it is either 5, 6 or 6, 5, and there is no other possibility. So here it will be 2 by 36. Now P4 is this product is 4. Now choices we have here is 1, 4, 2, 2 and 4, 1, and this is 3 by 36. And then we have P6, which is probability that this product is 6. Now it will be this 1, 6, 6, 1, 2, 3 and 3, 2. So it will be this 4 by 36. So clearly P1 is less than P30, is less than P4, is less than P6, and that's your option 1. Now here the question is, the probability of India winning a test match against West Indies is 1 by 2. So probability of India winning, it is 1 by 2, and assuming independence from match to match, we need to find the probability that in a match series, India's second win occurs at third test. I think it should be in a 3-match series. Now second win should occur at third test. So either it could be win, loss and win, or it could be loss, win and win. So these are the only 2 possibilities. Now first one is 1 by 2 into 1 by 2 into 1 by 2 and plus 1 by 2 into 1 by 2 into 1 by 2. So it is nothing but 1 by 4, and that's your option 2. Now the question is, in a multiple choice question, there are 4 alternate answers out of which 1 or more are correct. A candidate will get marks in the question only if he takes, a candidate decides to take answers at random. If he is allowed up to 3 chances to answer, he'll get marks in the question. Now, if it has 4 alternatives, then total number of possible choices are, for each option we have 2 choices. So it'll be 2 into 2 into 2 into 2. So there'll be 16 choices, but then there'll be this one choice when none of the answer is correct, which is not possible. So it should have at least one answer. So total choices we have here is 15. Now out of these 15, we have 14 wrong choices and 1 correct choice. So from these 15, he can try any 3. So it'll be 15C3, and among these 3, one of them has to be the correct one. So it'll be this 1C1, and then it'll be 14C2. Now this is 14 into 13 by 2, and this is 15 into 14 into 13, and this is 3 into 2. Now he'll cancel, 2 will cancel. So this probability is simply 3 by 15 or 1 by 5, and that's your option 3. Now here the first question is, two squares are chosen at random on a chessboard. Find the probability that they will have a side in common. Now two squares will have side in common when they are either horizontally together or when they are vertically together. Now for this case we need two connected horizontal squares. Now we have 8 rows. So out of these 8 rows, we can choose any one row. It is 8C1, and on any one row we have to select 2 consecutive squares out of 8 consecutive, and number of consecutive selections is n minus r plus 1. In the same way, from 8 vertical we can choose any one in 8C1 ways, and again from 8 squares 2 connected can be done in 8 minus 2 plus 1. So total case will be this into 2 divided by 64C2. Now this is 8 into 7 into 2, and this is 64 into 63 into 2. Now this is 8, 4, this is 2, and 7, 9. So this probability will be simply 1 by 18. So the probability that they have a side in common is 1 by 18, and that's your option 3. Now the second one is, 3 squares of normal chessboard are chosen. Find the probability of getting 2 squares of one color and 1 square of different color. So we have 2 cases. Either it could be 2 black, 1 white, or 2 white and 1 black. Now total number of choices is 64, C3. Now 2 black, so it will be 32 C2, and 1 white is 32 C1, and it will be same for 2 white and 1 black, so it will be this into 2. Now we can write this as 32 into 31 divided by 2 into 32 into 2, and here it will be this 64, 63, 62, and this is 3, 2, 1. Now this 2 and 2 will cancel. Now 32 into 2, it is 64. Now this 3 is 21, 31 into 2. Now this is 16. So this probability will be 16 by 21, and that's your option 1. Now this third case is, 3 squares are chosen at random. The probability that 2 are of one color. Now 2 of one color and 1 of different color. I think it's the same question, so we'll discard it. And then finally we have 4 squares are chosen at random from a chessboard. We need to find the probability that they lie on a diagonal line. So if we look at diagonal lines, so here we have 1, 2, 3 and 4. We have to choose 4 on a diagonal. So it could be this 4C4 plus 5C4 up to 7C4, and then 8C4, and after 8C4 again we'll have 7, 6, 5 and 4. So it'll be this into 2 and whole divided by 64 C4. Now we can also choose diagonal the other way. So this total case will be this 2 into this value. So we can write this as 4 into this summation n C4, where n varies from 4 to 7, and plus 2 into 8C4 divided by 64C4, and that's your option 4. Now the question is, each of the n urns contain 4 white and 6 black balls. The n plus 1th urn contain 5 white and 5 black balls. Now out of these n plus 1 urns, an urn is chosen at random
and 2 balls are drawn from it without replacement. Now both the balls turn out to be black. If the probability that the n plus 1th urn was chosen to draw the ball is 1 by 16, then the value of n by 2 is. Now either we can choose 2 balls from these n urns containing 4 white and 6 black, or we can choose this ball from this n plus 1th urn containing 5 white and 5 black ball. Now choosing this urn, probability is n upon n plus 1, and here the probability is 1 upon n plus 1. Now if we have chosen one of these urns, then probability of getting 2 black balls is 6c2 upon 10c2. Now in this case, this probability is 5c2 upon 10c2. Now it says the probability that n plus 1th urn was chosen is 1 by 16. So it is Bayes theorem condition. So we'll take this case in the numerator. So it will be 1 upon n plus 1 5c2 upon 10c2 by n upon n plus 1 6c2 upon 10c2 plus 1 upon n plus 1, and this is 5c2 into 10c2, and this value is 1 by 16. Now n plus 1 10c2 will cancel. We can write this as 10 upon, now 6c2 is 15. 15n plus 10 and will be equal to 1 by 16. Now we can write this as 15n and will be 160 minus 10, 150. So value of n is 10. Now we need to find the value of n by 2. Value of n by 2 is 5. So in this case, value of n by 2 is 5, and that is the answer to this question. Now the question is 5-digit numbers are formed in all possible ways using the digits 0, 1, 2, 3, 5, 6 without repetition. If one such number is selected at random, find the probability that it is divisible by 5. Now first we'll find how many 5-digit numbers altogether can be formed from these digits. Now for the first place, now it is a 5-digit number. For this first place, we have 5 choices. Now for the next one again, we have 5 choices. So it will be 5 into 5 and then 4 into 2 into 1. So it will be 120 into 5 and there will be 600 numbers. So altogether we have 600 numbers which can be formed from these digits. Now in the first case it says find the probability that number is divisible by 3. Now it will be divisible by 3 if sum of the digits is divisible by 3. Now if we look at sum of all the digits, so it is 1 plus 2 plus 3 plus 5 plus 6, there will be 12, 12 plus 5, 17. Now it will be a multiple of 3. If we discard this 2, then we are left with 0 plus 1 plus 3 plus 5 plus 6, or if we discard this 5, then we have 0 plus 1 plus 2 plus 3 plus 6, and there is no other possibility. Now here total number of 5-digit numbers that can be formed is factorial 5 minus all those numbers that start with 0. So it will be factorial 5 minus factorial 4, and here too will be factorial 5 minus factorial 4. So this required probability is 2 times factorial 5 minus factorial 4 divided by 600. Now factorial 5 is 120. 120 minus 24, it is 96. So it will be 2 into 96 upon 600, which is 8 by 25, and that's your option B. Now the second one is find the probability that it is divisible by 6. So for this, now we know that number is divisible by 3 if it is formed with either 0, 1, 3, 5 or 6, or with 0, 1, 2, 3 or 6. Now from these digits we have to form an even number. Now we have this first case when the number ends with 0. If the number ends with 0, then the number of such numbers is factorial 4, and if the number ends with 6, then it'll be factorial 4 minus factorial 3. Now factorial 4 is 24 and factorial 3 is 6. So there'll be simply 18. So it'll be 24 in this case and 18 in this case. Now here too, if the last one is 0, then we have factorial 4, which is 24. And if the last one is either 2 or 6, then it'll be this 18. So this probability will be this 24 plus 18 and then 24 plus 18 into 2 divided by 600. So it'll be 102 divided by 600, which is simply 17 by 100, and that's your option C. And finally, it is the probability that it is divisible by 5 but not divisible by 4. So for this third one, it should be divisible by 5. So we have two cases. Case 1, if the last digit is 5, if the last digit is 5, then we have to fill remaining 4 digits with 0, 1, 2, 3 and 6. Now for this first place, we have 4 choices. For the next one, again we have 4 and then 3 and then 2. So there will be 96. And then we'll have the numbers which will have 0. But then it should not be divisible by 4. So we can have 10. We cannot have 20. We can have 30. We can have 50. And we cannot have 60. Now, if it is 10 here, now we are left with 4 numbers, 2, 3, 5 and 6. So for this first one, we have 4 choices. Next one, we have 3 and then 2. So there will be 24 and it will be 24 for all the 3 cases. So this required probability will be 96 plus 3 into 24 upon 600, which is 168 upon 600, and we can simplify it to 7 by 25, and that's your option A. Now here we have 3 questions, 1, 2 and 3. Now the first question is, 2 non-negative integers are chosen at random from the set of non-negative integers with replacement. If the probability that sum of the squares divisible by 10 is p, then we need to find the value of 50p. Now, if we look at the squares of non-negative integers, then 0 square is 0, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, 7 square is 49, 8 square is 64, and 9 square is 81. Now it says sum of squares is divisible by 10. Now it will be divisible by 10 if we choose both the numbers which are 0. So it will be this combination 0, 0. Or if we choose 1, 9 or 9, 1. So it will be this 1 or 9, or it will be this 4, 6 and 6, 4. So, and then we also have this 5, 5. So it'll be this 5, 5 also. Now if it is 0, 0, now 0 is 1 by 10. Choosing another 0 is 1 by 10. Now 1 and 9. Now choosing 1 is 2 by 10 and choosing 9 is also 2 by 10, and then we have this 9, 1, so it will be this into 2 plus now 4, 6. 4 is 2 by 10, 6 is also 2 by 10, and then into 2 plus 5 and 5 it will be this 1 by 10 into 1 by 10. So this probability will be this 100, and then we have 1 plus 8 plus 8 plus 1, which is 18 by 100, and that is 9 by 50. Now we need to find the value of 50p.
So value of 50p is 9, and that is the answer to this question.
Now the question is, players P1, P2, P3 and P4, they play knockout tournament. It is known that if Pi and Pj play, then Pi will win if I is less than J. That means P1 is going to win all his matches. If they are paired at random for the first round, then the probability that P3 reaches the second round is. Now first we'll see from these four how many pairs of 2 and 2 can be made. Now it can be done in factorial 4 divided by factorial 2 whole square divided by factorial 2. Now it will be simply 3 ways. So there are altogether 3 ways in which they can be distributed in pairs of 2. Now these 3 will be either P1, P2 and pair of P3, P4, or it will be this P1, P3 and P2, P4, or P1, P4 and P2, P3. So these are the all possible combinations of pairs of 2. Now for this probability, we have total number of cases, which is 3. Now P3 can only reach semi-final if P3 is paired against P4, because against P1 and P2, he or she doesn't stand any chance. So this case is only when P3 is paired against P4, which is this case. So all these 3, only one is favorable. Now this probability is simply 1 by 3, and that's your option A.
Now here the question is, if m into n coins have been distributed into m purses, n into each, now we need to find the probability that 2 specific coins A and B, they are in the same purse. Now what we'll say is, suppose we have these coins distributed in these n purses, and there are m into n positions. Now in one of the purses, we'll have A. Now suppose A is present in this purse. For B to be present in this purse, B can be there in any one of the remaining n minus 1 places. So number of favorable places for B will be simply n minus 1, whereas total number of places will be simply m into n minus 1. So this probability that 2 specific coins will be found in the same purse is given by n minus 1 upon m into n minus 1, and that's our part 1. Now second part is, what the chance becomes when R purses have been examined and found not to contain either of the specific coins. Now here there will be 2 cases. Case 1, when both the coins, they are together, and this second case when they are in separate purses. Now this probability that they will be together, it is given by n minus 1 upon m into n minus 1, and the probability that they will be in separate purse will be given by 1 minus p, and will be m n minus 1 minus n plus 1 upon m n minus 1. Now 1 and 1 will cancel, so we can write this as n into m minus 1 upon m into n minus 1. Now when A and B are together and R purses have been examined, then the probability that they occur in the remaining m minus R purses will be given by m minus R by n. So total we have m choices, and the favorable cases, they're not present in the first R purses. Now in this case, say P2. Now P2 is when both of them, they are in separate purses, but still they are not in first R. So here it will be this MC2. So any 2 or these m, and then it will be this m minus R C2, which is m minus R minus 1 divided by 2. Now 2 will cancel, and here will be this m into m minus 1. So if they are together, then the probability that they'll be in R purses, it is given by m minus R by m. And if they are not together, then the probability that they'll be in remaining m minus R purses will be given by m minus R into m minus R minus 1 upon m minus 1. Now we need to find the probability that they are in the same purse
provided both of them, they are not there in the R purses that have been examined. So that means we have to find this probability that they are in the same purse when we have examined R purses. So now it becomes a Bayes theorem question. So this case it will come in the numerator. So it will be this n minus 1 upon mn minus 1 into m minus r by n. So it will be this n minus 1 upon mn minus 1 m minus r upon m plus this case where it is n into m minus 1 upon mn minus 1 into m minus r minus 1 divided by m into m minus 1. Now here m minus 1 and m minus 1 will cancel. N minus 1 and m, it will also cancel. So this required probability will be n minus 1 into m minus r, and the denominator will take m minus r common, and then will be this n minus 1 and plus n into m minus r minus 1. Now m minus r will cancel, so we can write this as n minus 1 upon, and this is n minus 1 plus mn minus nr minus n. Now this n and n will cancel, so this probability will be n minus 1 upon mn minus nr minus 1. And that is the answer to this question.
Now the next one is, every evening Mr. X either reads a book or watches TV. So this Mr. X, he either reads a book or he watches TV. Now probability that he watches TV is 4 by 5. So this is 4 by 5. Then probability of reading a book is 1 by 5. If he watches TV, then there is a probability of 3 by 4 that he falls asleep. So while watching TV, he falls asleep with the probability 3 by 4, and he does not sleep. This probability is 1 by 4. And if he reads a book, the probability that he falls asleep is 1 by 4. So while reading a book, he'll fall asleep with the probability 1 by 4. And he doesn't sleep with the probability 3 by 4. Now, on one evening, Mr. X is found to be asleep. Find the probability that he watched TV. So this again is a case of Bayes theorem. So he is found to be asleep. We need to find the probability that he was watching TV. So this probability that he was watching TV, if it is found that he was asleep, this is going to be, now this case in the numerator, which is 4 by 5 into 3 by 4 upon, now these two cases, which is 1 by 5 into 1 by 4 plus 4 by 5 into 3 by 4. Now this is simply 12 by 13, and that's your option B. And this third question in Bayes theorem is, a pack of 52 playing cards is counted with face downwards. If it is found that one card is missing, then one card is drawn and found to be red. Find the probability that missing card is red. So this missing card, it can be either red or black. The probability of it to be red, it is 1 by 2, and black is also 1 by 2. Now if the card lost is red, then probability of getting a red card, it will be 25 by 51. And if the card lost is black, then probability of getting a red card will be simply 26 by 51. Now it is known that the drawn card is red. Find the probability that missing card is red. So we have to find this case. So if drawn card is red, then find the probability that missing card is also red. Now we'll take this case in the numerator. So it will be this 1 by 2 into 25 upon 51 divided by this total case, which is 1 by 2, 25 by 51 plus 1 by 2 into 26 by 51. Now 1 by 2 will cancel, 51 will also cancel. So this probability will be simply 25 by 51, and that's your option A. Now here the question is, 3 vertices are chosen at random. from the vertices of a regular hexagon if P1, P2 and P3 are probabilities that triangle formed by three vertices is right angle, obtuse and acute angle, then which of the following is true? So we have this hexagon having 6 vertices. Now P1 is the probability that triangle formed by selected 3 vertices is a right angle triangle. Now if we select this vertex, then it will be right angle triangle if we choose either this vertex or this vertex. So there will be 2 triangles possible for any given vertex. So what we'll do is first we'll find total number of triangles that can be formed. Total number of triangles that can be formed is simply 6C3 and 6C3 is 20. Now in the first case, we need to find number of right angle triangles. Now number of right angle triangles is, first we choose any one vertex and it can be done in 6C1 ways. And once we choose any one vertex, then in order to form a right angle triangle, we have choice of 2 vertices. So they'll be into 2. So this required probability will be simply 12 by 20 or 3 by 5. So value of P1 is 3 by 5. Now we have a second case when it says triangle form is an obtuse angle triangle. Now again, if we choose this vertex, then it will be an obtuse angle triangle if we choose either this vertex or this vertex. Now if we look at obtuse angle triangle, then we can get obtuse angle triangle if and only if these 3 vertices they are consecutive. If the 3 vertices they are consecutive, then in that case we'll get an obtuse angle triangle. Now we have already studied in consecutive selection along a circle that if there are n points and we have to choose r consecutive points, it can be done in n ways. So number of obtuse triangles will be simply 6. So this probability P2, first one's P1, will be simply 6 by 20, which is 3 by 10. Now this is 0.6 and this is 0.3. Now we'll get an acute angle triangle only if we choose a triangle so that none of the side is the side of hexagon. Now in this case we have only 2 possibilities. So this P3 will be simply 2 by 20 and there will be simply 0.1. Now clearly P3 it is less than P2 and P2 is less than P1. So P1 is greater than P2 is greater than P3 and that's your option D. And if we look at this option C, which is P2 plus 3P3. Now P2 is 0.3 and 3 times P3 is also 0.3. So this is 0.6 and it will be equal to P1. So this option C is also correct. So the correct options are D and C. Now the question is 2 buses A and B are scheduled to arrive at a town central bus station at noon. The probability that bus A will be late is 1 by 5 and the probability that bus B will be late is 7 by 25. The probability that bus B is late, given that bus A is late, is 9 by 10. We need to find other probabilities. Now we are given that probability that bus A arrives late, it is 1 by 5 and probability that bus B is late, it is 7 by 25. Now it also is the probability that bus B is late, given that A is late, it is 9 by 10. Now this probability is probability BL intersection AL upon probability of AL and this is 9 by 10. The probability of AL is 1 by 5. So their intersection BL intersection AL will be simply 9 by 50. Now first we need to find this probability that neither bus will be late on a particular day. Now neither bus is late. That means probability AL naught intersection BL naught, and this probability is P AL union BL naught, and this is 1 minus probability of AL union BL. Now this is 1 minus PAL. This is 1 by 5 plus 7 by 25 minus 9 by 50. Now this is 1 minus 50, 10, 14 minus 9. So that will be 15 by 50, 3 by 10, which is 7 by 10. So this probability will be 7 by 10. That means this option A it is correct. Now the second one is bus A is late given that bus B is late. So we need to find this probability that AL by BL. Now this is probability of AL intersection BL upon probability of BL. Now AL intersection BL is 9 by 50 divided by 7 by 25. So this is 9 by 14. Option B is also correct. Now this third one is at least one of the buses late. Now in the first one we have already calculated this probability that neither bus will be late. So in C, this probability will be simply 1 minus the answer we get in this first part, which is 7 by 10, and it will be this 3 by 10, option C. Now here the question is 3 unbiased dice are rolled and the numbers on them are noted as A, B and C. The probability that the planes intersect along a line, intersect at one point, form a triangular prism is. Now if we look at these three equations, all these three equations, they are homogeneous equations. And if they are homogeneous equations, that means either it will have a unique solution or it will have infinitely many solutions. That means these three planes, they can never form a triangular prism. So the probability that they form a triangular prism is going to be 0. So that means this option C, it is correct. Now if we look at delta for these homogeneous equations, this delta will be this A, B, C, B, C, A and C, A, B. We know that we'll get this as 1 by 2 and then A plus B plus C will be A minus B square plus B minus C square plus C minus A whole square. And if it is equal to 0, we'll have infinitely many solutions. And if it is unequal to 0, then we have a unique solution. Now clearly this A plus B plus C, it can never be 0. So this delta, it can only be 0 if and only if A equals B equals C. Now if A, B, C, they are all equal, in that case, all the three planes, they'll be representing the same plane. So in that case also, they won't intersect in a line. All the three planes, they'll be identical planes. So that means this option A, it is incorrect. And for all the other cases, except for A equals B equals C, we'll get this condition that this delta is unequal to 0. Now this probability, it will be 6 into 6 into 6 minus those 6 cases when all A, B, C, they are equal, divided by 6 into 6 into 6. Now this is 210 divided by 216. If we divide by 2, we'll get 105 upon 108, and that's your option B. Option D is incorrect. So the correct options are B and C. Actually, we can further reduce this 105 upon 108. If we divide with 3, we'll get this as 35, and here will be this. So it should be 35 by 36. Now the question is, in a gambling between Mr. A and Mr. B, a machine continues tossing a fair coin until HT or TT on consecutive throws are obtained for the first time. If it is HT, then Mr. A wins, and if it is TT, then Mr. B wins. Then which of the following is or are true? Now if we look at first two tosses, then we'll get either heads heads, heads tails, tails heads, or tails tails. Now if it is heads heads, Mr. A is going to win, And if it is tails, then Mr. B is going to win. Now, what if we have HT? Now, in this, we know that if it is HT, then Mr. A is going to win. And if it is TT, then Mr. B is going to win. Now, what about HH? Now, if we get HH, then the machine is either going to throw heads or tails. Now, if you look at this sequence, then it could be HHT, or it could be HHHT, or it could be HHHHT. So, once we get any T, we will always get this HT. So, in this case also, Mr. A is going to win and Mr. B cannot win. Now, if you look at TH, we cannot get two T's, because whenever we get this first T, we'll get this condition of HT. So, in this third case also, Mr. A is going to win. So, are these four possibilities in the first row? Three of them favors Mr. A and one of them favors Mr. B. So, probability of Mr. A winning is 3 by 4 and probability of B winning is 1 by 4. That means options A and B, they are correct. Now, C is probability of Mr. A winning if first toss is heads. Now, if first toss is heads, then in that case, then Mr. A is sure to win this match. So, this probability is always going to be 1. So, this option C is correct. And D is the probability of winning Mr. A if the first toss is tails. Now, if the first toss is tails, then the probability of Mr. A winning is 1 by 2. That means option D is also correct. So, the correct options are A, B, C and D. Now, the question is, consider the sets A and B. The probability of getting an increasing function from A to B when a mapping is selected at random from the set of all mappings from A to B. Now, total number of mappings in this case will be, now for each of these three elements, we have 6 choices. So, it will be this 6 into 6 into 6 and there will be 206 possible mappings. Now, the first one is find the probability that we get an increasing function. Now, in order to get an increasing function, we need to select 3 out of these 6. So, it can be done in 6 C3 ways. And since they are to be arranged in increasing order, there is only one arrangement. So, it will be this 6C3 upon 216. Now, this is 5 into 4 upon 216, which is 5 by 54. And that's your option C. Now, the second one is probability of getting a non-decreasing function from A to B when a mapping is selected at random from the set of all mappings. Now, non-decreasing mapping or non-increasing mapping, we have already studied it on one of the previous videos. So, there the fundamental is, if we have two sets A and B, A containing n elements and B containing m elements, then number of non-increasing or non-decreasing functions, it is given by n plus m minus 1 Cn. So, in this case, this probability will be simply 3 plus 6 minus 1 C3 divided by 216. Now, this is 8C3, which is 8 into 7 divided by 216. Now, this is 7 by 27 and that's your option A. And then we have this third one, which is the probability of getting an onto function from B to B such that Fi is unequal to I when a mapping is selected at random from the set of all mappings from B to B. Now, here in this third question, we are considering mappings from B to B. Now, total number of mappings from B to B will be this 6 to the power 6. Now, are these mappings? We have to find all the mappings in which the function is an onto function and Fi is unequal to I. So, basically, this is nothing but derangement of 6 objects. So, it will be nothing but D6. Now, D6 is 265. So, it will be this 265 upon 6 to the power 6, which actually doesn't match with any of the option. But if we take this question as getting a function such that Fi is unequal to I, given that it is an onto function, then this probability, it comes out as D6 and number of onto functions from B to B will be simply factorial 6. So, if we take D6, which is 265 upon factorial 6, we'll get this result as 53 upon 144 and that's your option C. But the way the question is given, it should be this 265 upon 6 to the power 6.
Now the question is, consider a function f defined from the set 1, 2, 3 up to 13 to 1, 2, 3 up to 9, given that this function is surjective and non-decreasing, then probability that f7 equals 4 is. Now we have this set containing 13 elements. 1, 2, 3, 6, 7, 8 up to 13, and here we have 9 elements from 1, 2, 3, 4 up to 9. Now first we will find total number of ways in which this given function can be surjective and non-decreasing. Now it will be surjective and non-decreasing if this one, it is mapped to this one, and it may also map to 2 or 3 whatever, and this 13 it has to be mapped to 9. Now what we'll do is we'll say these first two, say x1, they'll be mapped to 1, then x2 they'll be mapped to 2, and then we'll have x9 which are mapped to 9. So x1 plus x2 plus x9, it must be equal to 13, where each of xi, it must be greater than or equal to 1. At least one of the elements should be mapped to each element in V, so that this function can be a surjective function. So in this case, we just need to find number of positive integral solutions. Now number of positive integral solutions is given by n minus 1 c r minus 1, which is nothing but 12c8. So total number of ways in which these functions can be defined so that function is both surjective and non-decreasing, it is 12c8. Now in the favorable case, we have this 7 which is mapped to 4. Now if 7 is mapped to 4, then in how many ways we can define this function? So for these first 4 elements we can write x1 plus x2 plus x3 plus x4, and it should be equal to 7, where each xi is, it is greater than or equal to 1. Now number of positive integral solutions in this case will be 7 minus 1, c 4 minus 1, and that will be 6 c3, and again from 4 to 9 we can write x4 plus x5 plus x6 plus x7 x8 plus x9, and that will be equal to 7, and here we will take this as x4 dash because we are talking about all the image of 4 from 7 to 13. Now again number of positive integral solutions will be 7 minus 1 c 6 minus 1, which is 6c5 or 6c1. So this required probability will be 6c3 into 6c1 upon 12c8, and that's your option D. Now the question is, if n different objects are distributed among n plus 2 persons, then the probability that exactly 2 persons will get nothing is. Now total number of ways of distributing these n objects among n plus 2 people will be, now for each object we have n plus 2 options. So total number of ways of distributing these n objects will be n plus 2, n plus 2, n plus 2, n times, and there will be n plus 2 to the power n. Now in this first case, when we have distributed them so that exactly 2 people get nothing, in this case we have to select are these n plus 2 which 2, and it can be done in n plus 2 c 2 ways. Now we are left with n objects and n people, and here since we have n people and n objects, so each person should get exactly 1 object. Now n different in n places can be distributed in factorial n ways. So this required probability that exactly 2 are left, it is given by n plus 2 c2 into factorial n divided by n plus 2 to the power n. Now this is n plus 2 n plus 1 factorial n, and this is 2 and n plus 2 to the power n. Now this is factorial n plus 1 upon 2, and this is n plus 2 to the power n minus 1. That means this option A, it is correct, and option D, it will be incorrect. Now in the second part it says probably that exactly 3 persons will get nothing. Now which 3? So first we'll select these 3 people from n plus 2, and which can be done in n plus 2. See 3 ways. Now we have n objects and n minus 1 people. Now out of these n minus 1 people, one of them will get 2 objects and remaining people will get exactly 1 each. Now which person gets these 2 objects? So we can select it in n minus 1, see 1 ways, and which 2 objects? So from the n we can select it and see 2 ways. Now we are left with n minus 2 people and n minus 2 objects, which can be arranged in factorial n minus 2 ways. Now this required probability will be total number of cases, which is n plus 2 to the power n. So this probability is n plus 2c3 into n minus 1 nc2 n minus 2 factorial upon n plus 2 to the power n. That means this option B is correct and option C is incorrect. So the correct options are A and B. Now the next one is 5 ordinary dice are rolled at random and sum of the numbers on them is 16. If K is the probability that number shown on each is any one from 2, 3, 4 or 5, then 49K is. Now this is a conditional probability question. We have to find the probability that number shown is any one from 2, 3, 4 or 5 when we are given that the sum of numbers on it is 16. Now what we'll do is first we'll find the total number of ways in which we can get sum of numbers on 5 ordinary dice as 16. Now we have to use binomial, so we need to find coefficient of x to the power 16 in this binomial expansion of x plus x square plus x to the power 6 to the power 5. Now we can take x to the power 5 common, so it will be x to the power 11 in 1 plus x up to x to the power 5 to the power 5, or coefficient of x to the power 11 in 1 minus x to the power 6 to the power 5 into 1 minus x to the power minus 5. Or we can write this as coefficient of x to the power 11 in 1 minus 5 x to the power 6 into 1 minus x to the power minus 5. Now for this, what we need is, we need 1 into coefficient of x to the power 11 in 1 minus x to the power minus 5, and then minus 5 into coefficient of x to the power 5 in 1 minus x to the power minus 5. Now this is 11 plus 5 minus 1, C11, and then minus 5 into 5 plus 5 minus 1, C5. So it will be 15C4 minus 5 into 9C4, and which is 1365 minus 5 into 9C4, which is 126. So this value will be 735. So there are 735 ways in which the sum of numbers on 5 dice will be 16. That's a number of elements in case sum is 16. Now our favorable event is when we get 16 from these 4 numbers. So that means now we have to find coefficient of x to the power 16 in, now we are given numbers 2, 3, 4 or 5. So it will be this x square plus x cube plus x4 plus x to the power 5 and this to the power 5. Now here we'll take x to the power 10 common. So we need coefficient of x to the power 6 in 1 plus x square plus x cube to the power 5, or we can write this as coefficient of
x to the power 6 in 1 minus x to the power 4 to the power 5 into 1 minus x to the power minus 5. That is coefficient of x to the power 6 in 1 minus 5x to the power 4 and then 1 minus x to the power minus 5. Now here we can write coefficient of x to the power 6 in 1 minus x to the power minus 5 and then minus 5 into coefficient of x square in 1 minus x to the power minus 5. Now this is 6 plus 5 minus 1 C6 and then minus 5 into 2 plus 5 minus 1 C2. Now this is 10 C6 which is 10 C4 and then minus 5 and here it is 6 C2. Now 10 C4 is 210 minus 5 and 6 C2 is 15. So this value will be 210 minus 75 which is 135. So that's your favorable cases. Now we can work out this probability. So this probability will now be 135 upon 735 which is 9 by 49. And the question it says this probability is k and we have to find the value of 49k. So if we look at this 49k, the value of 49k is simply 9. So answer to this question is simply 9.